Hi, and welcome to this learning path on Hyperledger's suite of frameworks and tools. We start off by taking a look at some of the prerequisites. First of all, some fundamental understanding of distributed computing will be very helpful. The architecture of most of the Hyperledger frameworks does involve several different components, each of which have their own specialized function and which are constantly communicating with each other. And having some knowledge about distributed computing will definitely help you understand exactly how the Hyperledger frameworks work. Another prerequisite is a basic knowledge of data structures. This is primarily required to understand the concepts around blockchains and to some degree also around smart contracts. And a final prerequisite is familiarity with application development. Although this is not a strict requirement for this learning path, which focuses primarily on giving you a conceptual understanding of Hyperledger, a coding background will give you a better understanding of smart contracts and what their limitations and benefits are. So before we move along, just a little tip. When it comes to learning about blockchains, there are many new terms which you will need to get used to. All of this can seem a little overwhelming, which is why my aim is to help you understand each of these terms by means of reinforcement. So I will try to repeat the concept around a certain term each time it is used in order to explain something new. However, if you do have trouble remembering what exactly it is, I do urge you to rewind the video and revisit where that term was defined in the first place. And with that, we can now move ahead with our course. And we will start off by explaining what exactly a blockchain is. So a blockchain can be thought of as a list of records which are stored across a sequence of blocks, and that these blocks are chained together using cryptography. So what exactly does this boil down to? For that, we can break down this definition into its components. So there are essentially 3 points which are of significance here. Firstly, that a blockchain happens to be a list of records. These records can be thought of as being similar to the records which are stored in database tables. And in the case of blockchains, they are very often used in order to store details of transactions. Another component of blockchains is that all of these records are stored across a sequence of blocks. So while in a database table, you have a single table which contains all of these records, in a blockchain, the data is essentially partitioned across a number of different blocks. And once you have your data split across these blocks, all of the blocks in turn are chained together in order to maintain an ordering of the blocks. So these 3 characteristics give you some idea of what a blockchain is, but we can now try to visualize this in order to get a better understanding, starting off by focusing on the fact that a blockchain is essentially a list of records. So in this case, we have a total of 9 records which very much look like the contents of a database table. In most blockchains, as I mentioned, the records will contain the details of transactions, but for this particular example, assume that the data which we need to store in a blockchain is essentially what you have in front of you. From the first column, do note that there is a sequence of the records which needs to be maintained by the blockchain. So now that we have our list of records, we will now see how a blockchain will store this data across a sequence of blocks. So a single list of 9 records can potentially be broken up into 3 different blocks. So for example, the first block will include the first 3 records, a second block will include the next 3, and then of course the final 3 records in our list will be placed in a third block. So we have an even split of the records over here, which is not necessarily the case in a blockchain. But this example does convey to you that all of the data which is stored in a blockchain is essentially split into these block units. An important feature here is that within each of the blocks, the records themselves are ordered. An important feature of a blockchain is that an ordering of the records needs to be maintained overall, which means that the ordering should take place not just within the block, but across the blocks as well. And this brings us to the third point in our definition of a blockchain, where the blocks are chained together. So to maintain the overall ordering of all of the records, we need to make sure that an ordering of the blocks occurs as well. And these blocks are ordered by essentially chaining them together into a sequence. So by connecting the block on the left to the one in the middle, and then following that, the middle block to the last block, we essentially maintain a sequence of blocks, and within them a sequence of records, which gives us an overall sequence of all of the records which we have stored here. So overall, you can say that a blockchain is essentially some way to store data. And in a very simplistic way, that is an accurate definition. However, a blockchain does have its own characteristics. First of all, it is a sequence of records which is continuously growing. That is, new blocks are continuously being added to the blockchain, and you must assume that this growth will never stop. Additionally, a blockchain is not maintained by a single machine or some single source, but by a network of nodes. So the responsibility of maintaining a blockchain is effectively a team effort. And whenever there is a team involved, it is crucial for the members of the team to have some way to reach a consensus. In the case of a blockchain, the consensus the members must reach is what should be stored within the blockchain. So while these characteristics do correspond to the ones for many decentralized systems, it is the next two factors which distinguish blockchains from many other ways of storing data. So the information which is stored on a blockchain can be considered to be immutable. That is, once the data has been written to the blockchain, it cannot be modified or overwritten. And this is because if any of the parties maintaining the blockchain were to attempt this, then they will be caught. And the reason for this is that every single record within the blockchain can be verified. So these are the crucial characteristics which you must keep in mind with regards to blockchains. Once the data has been written to it, it cannot be modified in any way. And this is because there are mechanisms in place to ensure that any such modification will be very easily caught by any of the participants in the blockchain network. This has the effect of enabling a great degree of trust among the nodes which participate in a blockchain network, since they have every incentive to behave honestly, and any attempt at manipulation will be very easily caught. The specific implementation of blockchains which allows this immutability and verifiability of records is something we will explore just a little later. But we now zoom in on one of the points which we just discussed, which is what constitutes consensus among the nodes which maintain a blockchain. So the first point which the nodes must agree upon is what exactly are the contents of the records which make up the blockchain. So if a particular record represents a transaction involving the transfer of n units of an asset from account X to account Y, then all of the nodes must be in agreement about the source of the transaction, the recipient, as well as the quantity being transferred. So once you have a number of different records and the nodes are in agreement about their contents, they also need to agree on the overall ordering of those records. So it is these two criteria which essentially constitute the consensus to be reached in a blockchain network. And there are several different algorithms available in order for the nodes to reach such a consensus. And with that, you should now have a better understanding of this definition of what a blockchain is. In the previous video, we covered the fact that a blockchain is something which is maintained by a number of different nodes. If you were to consider the data which is stored in a blockchain, essentially a sequence of records, to constitute a ledger of data, then you can say that the approach adopted by blockchains is that of a distributed ledger, where each of the nodes which maintain the blockchain have a copy of the ledger itself, and there are a few advantages to that approach. To fully grasp those benefits, however, we take a look at the other option, which is to have a centralized ledger. So what exactly does it mean to have a centralized ledger? Well, consider that you have a number of different records which store important data, and that there are several parties who would wish to access that data. If you were to store the data, essentially the ledger of records, in a single central location, and that all of the parties who wish to access the data need to get in touch with that central location, then what you end up with is essentially a centralized ledger. So in the example which you see on the screen in front of you, there are 6 different parties who are accessing the centralized ledger, which is stored in one single location. So what are the benefits of such an approach? Well, having a centralized ledger is rather easy to implement. You can provision a single node in one location and then load it with the contents of the ledger and then leave it open for others to access it. Such a centralized ledger is also rather easy to maintain since you only have one copy to update. So if data gets added or updated within the ledger, then all of the changes only need to be performed once. That is, on the one node which contains the ledger. This also means that the update operations don't require any communications between the nodes. Once the update has been made, the details of the update or even the fact that something has changed need not be propagated, and those who make a request to access the ledger after the update will then get the new data. So the overall simplicity of having a centralized ledger does come with a few drawbacks. A very important one being a single point of failure. If the node which hosts the contents of the ledger were to fail for some reason, then nobody has access to the ledger and they will need to wait until the node is brought back up. Another important issue, even when the node is up and running, is to do with latency. Consider that you have a number of parties who are geographically far away from where the ledger is stored. Each time they wish to access the contents of the ledger, they may need to wait a number of seconds, and this could be an unacceptable level of performance for any system. So in order to tackle these drawbacks of a centralized ledger, we can of course make use of a distributed one. In this case, a number of different participants will have their own copy of the ledger. One characteristic of a distributed ledger approach is the amount of communication between the nodes which maintain the ledger, which is represented in here by means of the number of communication lines. And with that, we move along to the benefits of the distributed ledger approach, which are essentially the problems with the centralized ledger one. Specifically, distributed ledgers offer fault tolerance. Since there are multiple copies of the ledger, if one or even a handful of the nodes were to go down, then copies are still available from the other nodes. If the nodes which maintain the distributed ledger happen to be geographically spread out, then this can significantly reduce the overall latency when it comes to accessing the data in the ledger. Nodes which maintain the copy of the ledger only need a local lookup to access its contents, and even those parties which don't actively participate in the maintenance of the ledger only need to do a lookup on the nearest copy of the ledger. Which brings us now to the drawbacks of the distributed ledger approach, one of which is the amount of complexity required in order to keep the ledgers in a consistent state. That is, to ensure that all of the nodes which maintain the ledger have the exact same copy of it. To achieve this, the nodes need to be able to communicate with each other on a regular basis. And the greater the number of nodes which maintain the ledger, the greater the amount of communication required. Now, depending on the implementation, if an update has been made in one of the copies of the ledger, they will need to be propagated to each of the other copies, and this could take some time, especially if the nodes happen to be rather spread out. In such cases, there will be points where the local copy of the ledger may not be entirely up to date. So with a distributed ledger, what you gain in terms of fault tolerance and performance are offset to some degree by the overall complexity and the occasions where you may be working with some stale data. There are many situations, however, where a distributed ledger is the preferred option, and this very much applies with blockchain networks as well. So in this case, It is the chain of blocks, that is, the blockchain, which is the distributed ledger, and all of the participants which maintain that blockchain are the nodes which make up a blockchain network. So a blockchain network is essentially an implementation of a distributed ledger where you have a number of different nodes which maintain the blockchain, and they need to be in constant communication with each other to ensure the consistency of that blockchain. And with such a setup, let us take a closer look at the nodes which make up the blockchain network. Now, each of these nodes does have some role to play, and there are different implementations of blockchains out there where each of the nodes could be equals, or they may have specialized functions as well. But generally speaking, there are certain characteristics for the nodes in the blockchain network. So each of these, as we have seen, are considered participants in the blockchain network, and the nodes may have access to at least some of the blockchain data. That is, they will be able to access the records which are stored on the blockchain. In addition to reading from the blockchain, some of the nodes may also have the ability to write to it. And since the records which have already been written to a blockchain cannot be modified, modification of a blockchain essentially means adding new records. And in order to ensure that the contents of a blockchain have not been modified, nodes will also have the ability to verify the contents of the blockchain. So overall, the nodes which make up a blockchain network do have some role to play. The variety and the scope of those roles is something we will explore later in this learning path. In the previous video, we covered both a centralized ledger as well as a distributed ledger approach, and then discussed the benefits and drawbacks of each of those approaches. We will now take a closer look at a distributed ledger and then explore why a blockchain is the ideal way to maintain a distributed ledger. This explanation will be done by means of a real-life example. Let us consider the case of supply chain management, where the participants which are involved in a supply chain will need to make use of a distributed ledger to record their transactions. In our example supply chain, there are 4 different participants. So out of these, the first is a factory which may manufacture a number of different products. Once the factory is done with the manufacturing, they will sell those products over to a distributor, and the distributor in turn will hand over the products to a wholesaler. From here, the product will finally make its way to a retailer who will display the product on shelves within their stores. In real life, of course, there will be a number of different distributors, wholesalers, retailers, or even factories. But for the sake of our example, we assume that there is just one of each. You will note that in the case of a product making its way from the factory to the retailer, there are 3 different handoffs, and each of these will require a transaction which is recorded on a ledger. The way things are set up today, in many such instances, each of the participants will maintain their own individual ledger. So it is not a common distributed ledger which they collectively maintain, but each of them will have their own list of transactions which they record in their books. Now, in the case of such a supply chain, each of the participants has their own list of considerations. But for now, let us look at it from the point of view of a retailer who will wish to have a lot of control over the entire supply chain. For example, the retailer will want records of each and every product which have been sourced from the multiple factories, which of those have been handed over to which distributors, and then in turn to the wholesalers which make up the supply chain. In short, the retailer will want to know where exactly the products have been sourced from and will want to record the exact route taken by those products to reach their stores. One of the reasons why a retailer will want to do this is to ensure that the products have been sourced from the correct factories. Since it is the retailers who are the ones facing the consumers, they are the ones who know which products sell well, and they will want to make sure that the products do come in from factories which have a certain standard of quality. Another important consideration for retailers is to keep track of the products which are on their way to the stores. The retailer will need to make sure that they never run out of a particular product. So if they are able to keep track of where each of the products are in the supply chain, they will know when exactly they are scheduled to arrive at a store and then can plan accordingly, potentially by placing more orders of a product. And another important consideration for the retailer is that they will want to identify any issues which might arise in the supply chain. It is possible that a certain batch of a product did not quite meet their quality standards, and they will need to identify what exactly went wrong. Was it a particular factory which is to blame because of faulty machinery, perhaps? Or was it a distributor who did not store the product properly or was careless during its transportation? All of these will be easier to debug if the retailer had access to all of the steps involved in the supply chain, from the manufacturing of a product in the factory to their handovers to distributors and wholesalers. Moving on now from the considerations of the retailer to that of any of the other participants. So each of them will need to make sure that the products which came to them and then they handed over to someone else further up the supply chain do indeed make their way to the intended retailer and not, for example, into the black market. They will also need some way to record all of the transactions in the supply chain, which will not only record the route the products took to get to the retailer, but can also be used in order to resolve any disputes which might arise. So having a common ledger which is distributed will help in such instances. Another consideration for all of the participants in a supply chain is to regulate who exactly can view all of the details in a transaction. For example, it is possible that a wholesaler may be selling the same product to different retailers at different rates. They may have their own reasons for doing so. Perhaps one of the retailers has been a long-standing customer and has always been prompt with their payments. So a wholesaler may want this particular retailer to have a better rate, but will not want the other retailers to be aware of it. So a degree of confidentiality with the transactions is also required. So while these are some of the abstract requirements for the participants, in order to fully grasp why exactly these are necessary and how exactly this can be achieved, we will be taking a look at a concrete example, but that will happen in the next video. In the previous video, we took a look at some of the requirements for various participants in a supply chain. While the retailer may have their own specific set of considerations, there are common factors which apply to all of the participants in the supply chain. We will now take a look at a concrete example where all of the members who make up a supply chain can benefit from having a common distributed ledger which they can all rely upon. Consider a case where a factory in the supply chain happens to have a dispute with the distributor it sold some products to. Each of these entities will have their own copy and own independent copy of a ledger where they record their transactions, and the distributor claims that a particular batch of products was never delivered to them. This is, however, denied by the factory, and when they go and consult their own independent ledgers, each person's claim is supported by what is there in their own ledgers. So when you have such a scenario, how do you determine the truth? Who is correct, the factory or the distributor? Well, a solution to this is not to have each of the entities maintain their own independent ledgers, but to have them maintain a distributed ledger as a team. So it's not just the factory and the distributor, but if all of the participants in the supply chain came to an agreement that they should maintain a common distributed ledger, then such a dispute would never arise since all of them can see exactly the transaction which took place. If the factory did indeed sell the batch of products to the distributor, it will be recorded on the ledger. And if there is no such record, it means that the product was never handed to the distributor in the first place. However, such a setup will work only if there is some mechanism to ensure that the ledger cannot be tampered with. So all of these participants in the supply chain can work in a system of trust only if they all happen to have a common ledger which they know is tamper-proof and is the universal source of truth. So what are the ideal qualities of such a ledger? That it must be immutable, and that each of the records which make up the ledger should also be verifiable. From these two qualities, let us now focus on the immutability of a ledger. This means that once a record has been written to the ledger, it cannot be removed or modified in any manner. If there is an attempt made to change the contents of the ledger, that is to modify or remove some of the records, then this is something which can be easily detected by the other participants who maintain that ledger. And this detection is possible if all of the records on that ledger happen to be verifiable. Just to summarize, the verifiability of a ledger means that it can be confirmed that all of the records which make it up are indeed accurate. And in case there is some tampering which has been performed, it is very simple to detect this fact. And these qualities of immutability and verifiability of an ideal ledger will be familiar to you because these are the exact characteristics of a blockchain, which we covered a little earlier in this course. Which now brings us the question, how exactly is this immutability and verifiability achieved in a blockchain? Well, for that, we will revisit exactly what a blockchain is. We saw that a blockchain can be summed up as a list of records which are split across a sequence of blocks. Within each of the blocks, there is an ordering of the records, and then in order to maintain an ordering of the blocks themselves, they are chained together. So the immutability and verifiability of the records in a blockchain is in fact achieved by the nature of this chaining of blocks. And how exactly are these blocks linked together? The answer to that is using cryptography. We can now take a closer look at the implementation of this cryptographic link. So each of the blocks in the blockchain will consist of a number of different details, and this includes a cryptographic hash of the previous block in the blockchain. In addition, a block will also include a timestamp, which represents the time at which the block was added to the blockchain. And of course, it will contain a number of records. And in the case of most blockchain networks, these records store transaction data. And then in addition, there can also be some metadata around the block. In most cases, you can think of the transaction data as being the real data which is stored in the blockchain network. All of the other information which is available is simply some way to make it easier to access the transaction data or to ensure that that data has not been tampered with and can be relied upon. And it is this cryptographic hash of the previous block which not only links the current block to the previous one, but also serves the security purpose which is required of a blockchain. To be precise, it is this cryptographic link which ensures that the transaction data in any block cannot be altered after the fact. And tampering with this information is something which is not theoretically impossible, but is effectively so because this requires altering all of the subsequent blocks in the blockchain. And not only that, it will also require a consensus from all of the other nodes which make up the blockchain network. This is something we will be exploring in more detail in the next video. But for now, it is enough to know that it is this cryptographic link between the different blocks in the blockchain which ensures that each of the transactions which are recorded in the blockchain are both verifiable and also immutable or permanent. In the previous video, we touched upon the fact that the security in a blockchain, essentially its immutability and the verifiability of the records which are stored on it, is assured by means of the cryptographic link between the blocks which make up the blockchain. This cryptographic linking is achieved by means of including a cryptographic hash of the previous block within each new block added to the blockchain. In this video, we will take a look at what exactly is meant by a cryptographic hash and how this ensures that the contents within a particular block cannot be tampered with. We begin by reintroducing the definition of a blockchain, which we saw earlier. That is a list of records which are stored across a sequence of blocks, and those blocks in turn are chained together using cryptography. So the three components which make up that definition include the fact that it's a list of records, that they're stored across blocks, and what we will focus on now is the fact that these blocks are chained together and that the technique which is used for this chaining is a cryptographic hash. So the example we have been taking a look at so far is this list of 9 records which are split across 3 blocks. And the question we had posed earlier was, how exactly is the relationship between the adjacent blocks defined? And we also saw the answer to that question, which was by means of a cryptographic link. So each block in a blockchain includes a lot of bits of information, the most important one being the transaction data which it stores. However, to ensure the convenience as well as the immutability of this transaction data, there are a number of other bits of information which we store within the blocks, and this includes the cryptographic hash of the previous block. It is now time for us to focus on the concept of a cryptographic hash. And for that, we take a look at what exactly a hash algorithm does. It begins with some form of input message. This input will be fed into some hash function, and then the output which is produced by that function is referred to as a hash value. We can now take a closer look at this hash value, which is the output of a hashing algorithm. And this is something which is often referred to by many other names. So the different terms used for the hash value include a message digest or simply just a digest. It can also be called a digital fingerprint of an input message or even a checksum. Now you may have come across a lot of these terms, if not all of them, but in the end, all of these are in fact different forms of hash values. The specific term which is used depends on the context in which it is utilized. However, the purpose for computing such a hash is always the same, to ensure the integrity of the original message. And in a similar manner, a cryptographic hash can ensure the integrity of a blockchain. There are, however, many different kinds of hash functions which can be used, and they're not all meant to ensure the integrity of the input. In the case of blockchains, however, this integrity is very important for us. So let us consider the properties of an ideal hash function when it comes to blockchains. For one, it must be rather simple to compute the hash value given the input message. This is an operation which will need to be performed frequently, which is why it is good not to use too many compute resources or even time in order to calculate this hash. Another important characteristic is that this hash function should have a low probability of producing hash collisions. A hash collision is when two different input messages end up having the same output hash value. So these are very common requirements of a hash function in many different use cases. What is needed from a cryptographic hash function is similar, except with one additional property. So not only should it be easy to compute a cryptographic hash given an input message, and that it should have a low probability of generating hash collisions, such a function should also make sure that it is impossible for any malicious entity to recreate the original message given only the output hash value. So with that, we can define a cryptographic hash as a special form of hash function in which it is impossible to recreate the original message given only the output. So while we saw previously that a hash algorithm will take in an input message, apply a hash function in order to produce an output hash value, in the case of a cryptographic hash algorithm, this will ensure that this hash value cannot be used in order to recover the original input message. In other words, it should not be possible to reverse engineer the input message given the output hash value. Which takes us back to the contents of an individual block in a blockchain. So the cryptographic hash of the previous block, which is included here, cannot be used in order to reproduce the contents of that previous block. So we have an idea of what exactly a cryptographic hash algorithm does. But what exactly is an example of a cryptographic hash algorithm? Well, the most commonly used one is SHA-256. So this comes under the SHA-2 family of hashing algorithm, where SHA is an abbreviation for Secure Hash Algorithm. This is something which was designed by the National Security Agency in the United States. So it is something which has been thoroughly researched and, at least as far as we know, has not been broken yet. So the SHA-2 is in fact a family of hashing algorithms, and the SHA-256 algorithm belongs to this family. It is available for anybody to use for free and is also the most commonly used algorithms in many blockchain implementations. The number 256 in the name represents the number of bits in the output digest. So 256 bits translates to 32 bytes, and when expressed as a hexadecimal string, it will always be 64 characters in length. So how exactly is this used? Well, consider the string wind with an uppercase W. Using a SHA-256 hash generator, which is freely available on the internet, we can calculate its hash value, and this 64 character string which you see below is what is produced by the algorithm. Given SHA-256 is a cryptographic hashing algorithm, there is no way to recover the value wind, which is the original input, from simply the output hash value. A rather important characteristic of a cryptographic hashing function is that even a minor change in the input can produce a drastically different output. As an example, take this particular hash value of the string wind with a capital W and notice some of the characters here. And then following that, take a look at the hash value of the string windy. So we have merely added one character to the input, but the output hash is entirely different from what we had previously. So just because two hash values look rather similar does not mean that the input which produced them have any relation to each other. Another very important characteristic of a hash function is that the size of the output hash will always be the same, irrespective of the size of the input. In the case of a SHA-256 hash, you can be assured that the output will always be exactly 256 bits in length. So if your input message happens to be the string wind or windy, or even the contents of an entire book or the entire works of Shakespeare, for example, then the output which it generates will always be exactly 256 bits or a 64 character hexadecimal string. So one thing to keep in mind when using a cryptographic hash, or any hash function for that matter, is that it is possible for multiple inputs to produce the same hash output. As mentioned earlier, such an occurrence is described as a hash collision, and given that the size of the output generated by a hash is always fixed, the output can only take a finite range of values, and this contrasts with the inputs to a hash function, whose range, of course, is infinite. So while a good hash function will generate very few hash collisions, these are by no means impossible. But the reason why cryptographic hashes do find use in security is that these collisions are pretty much impossible to predict. In the previous video, we saw exactly what a cryptographic hash is, and we also covered the fact that once you have the output of a cryptographic hash, it is, for all practical purposes, impossible to reverse engineer the original input. In this video, we will see how that particular characteristic of a cryptographic hash does ensure the integrity of a blockchain. So we have previously seen that a blockchain consists of a list of records which have been split up into a number of blocks, and that these blocks are linked together by means of a cryptographic hash. We can now zoom in just a little bit to see exactly what this looks like. So here we have our chain of blocks, which makes up the blockchain. And just to simplify the view, we have shown that each of the blocks includes a collection of transactions as well as a hash of the previous block. So you see here that the hash of the first block is one of the contents of the second block in the blockchain. That hash, along with all of the other information within that second block, will be used as input in order to generate the hash of that second block, which in turn becomes one of the pieces of data which is included within the third block. And this chaining goes on for the entire blockchain. The only block in the entire blockchain which does not include a hash of the previous block is the first one, and this is something which is also known as the genesis block. So with this form of arrangement, you can see exactly why this structure is called a blockchain. You have a sequence of blocks which are essentially chained together by means of having a cryptographic hash of the previous block within them. And the reason for including this cryptographic hash is to ensure the integrity of the blockchain. To understand exactly how that works, let us consider what happens when someone tries to tamper with one of the blocks in the blockchain. In our example, we try to modify the contents of a transaction in the first block or the genesis block. Now, the effect of this is that the hash of the first block will be completely different. We have seen previously that even a minor change in the input to a hash function is likely to produce an entirely different output. So even a minor change in the transactions of the first block is likely to produce an entirely different hash. And anyone who is trying to verify this blockchain will immediately notice that the hash produced of the first block is very different from the cryptographic hash of block number 1, which has been included in block number 2. In order to avoid this inconsistency, perhaps the malicious party who has altered the contents of the transactions will modify the second block as well so that it includes the newly computed value of the first block. But then, of course, the hash which has been computed for block number 2 will also need to change, which in turn will affect the contents of block number 3 as well. And this, of course, will keep going on until the end of the blockchain. So, if you were to tamper with one of the transactions in one of the blocks of the blockchain, to keep your blockchain consistent, you will need to modify each of the subsequent blocks in that blockchain. And if this blockchain is maintained as a decentralized ledger, then all of the other nodes in the network will instantly realize that the hashes which they have of the blocks are completely different from your hash. So for you to tamper with the blockchain and not get caught, you will need to do so in such a way that your revised block ends up producing the same hash as it did previously. And this is something which is theoretically possible since you can have hash collisions. However, we have also learned that it is impossible to reverse engineer a hash. So even though you know exactly what output you're looking for all practical purposes, it is impossible for you to figure out a different input which will produce that same output. We have touched upon the fact that hash collisions are pretty much impossible to predict. All of these characteristics of a cryptographic hash has the effect of ensuring that any attempt at modifying an old record in your blockchain can be very easily detected. So this gives a blockchain the two very important characteristics which we have discussed: immutability and verifiability. So what implication does this have in the real world? Well, for that, we revisit the example of a retail supply chain which we saw previously in the course, where you have some goods which move from a factory over to a distributor, to a wholesaler from there on, and then finally to a retailer. All of the transactions which take place in the supply chain will be recorded on a distributed ledger, which will be implemented as a blockchain. So each of these 4 entities has a copy of the blockchain and are collectively responsible for maintaining its contents. And in the case of any dispute between 2 participants, where we consider a case of a factory and a distributor not agreeing on whether a particular batch of goods was delivered, they can also see who exactly was right by referring to the blockchain which they are collectively managing. And they can entirely trust that this blockchain is both immutable and verifiable. If there is a record of a transaction where a factory handed over a batch to the distributor, then both of them will need to agree that this is the fact, since neither party can blame the other for tampering with the data. So when it comes to resolving disputes in a blockchain system, it is the contents of the blockchain which decides who exactly is right. So this is one of the crucial reasons why blockchains offer so much promise. The immutability and verifiability of its contents ensures that all of those participating in a blockchain network can trust what is within that blockchain, and there is absolutely no incentive for someone to try to tamper with its contents. And all of this is possible thanks to the nature of cryptographic hashing. So while cryptographic hashing does ensure that the data cannot be tampered with, what exactly is the purpose of having this data stored as a chain of blocks rather than just a single list? This is something which we will explore in the next video. In the previous video, we covered the fact that since a cryptographic hash is impossible to reverse engineer, it can be used in order to ensure the integrity of a blockchain. In fact, a cryptographic hash ensures the integrity of any data, which is why it is often used as a message digest or a checksum when you're downloading files from the internet, for example. And since we essentially want to ensure that our list of records has not been tampered with, what exactly is the purpose of storing those records as a chain of blocks rather than as a single long list? This is what we will now go ahead and explore. So we begin by once again viewing what a blockchain is. So we know now that it is a list of records which have been arranged into blocks which are cryptographically linked. At the heart of it, a blockchain is essentially a list of records, and this is simply another term for a ledger. And if this ledger happens to be distributed across a number of different nodes, then this is a distributed ledger. Now, in most blockchain implementations, including the Hyperledger Frameworks, the list of records is in fact a list of transactions. So each of the individual records represents a single transaction. And then using our retail supply chain example, the transactions which will be recorded in this distributed ledger could be the handing over of a product or a batch of products from one of the participants to another. So a typical transaction will involve a sender, a recipient, and a quantity of an asset. So out of the 4 participants here, let us just consider 3 of them. And we know that a distributed ledger means that everyone in the network shares the same ledger and are collectively responsible for its maintenance. So we have 3 copies of the ledger here, one for each of the 3 participants. You will see that the ledger consists of about 1 million transactions, and that for every transaction there is a sender, a recipient, and a transaction amount. You will also notice that from what we can see here, all 3 of the ledgers are identical. Now, the ledgers can be considered identical only if they contain the exact same transactions in the exact same order. We have covered previously that it is these 2 criteria which the nodes need to arrive at a consensus on. So with such a setup, we have a distributed ledger, which means that there is no single point of failure. However, this comes at the cost of more effort required in order to maintain the ledger's consistency. That is, we need to make sure that the records have the exact same contents and that the records are in the same order across all of the nodes which make up the blockchain network. But how exactly can we make sure of these? Well, one simple solution is to make use of hashing. This is a much better option than individually comparing all of the records and their ordering. So how exactly will this work? Well, one way to do this is for each of the nodes to not only store the entire contents of the ledger, but to also calculate the hash of the full ledger. We can now take a look at exactly how this would be implemented. So moving back now to the 3 copies of the ledger which we have, each of the nodes will now calculate a hash of the full ledger. And you can see that both A and B happen to have the same ledger, which is why the hash which they have calculated is exactly the same. But you will also see that in the case of C's ledger, there is at least one transaction which is different, specifically the last one which you see, where the amount which is transferred from X to Y is 45 in the case of C, whereas it's 50 in the cases of the other 2 participants in the network. So each of the participants can now exchange their hashes, and they will realize very quickly that the hashes are different. But we can assume that in the case of node C, there is a discrepancy, but this may not be due to any malintent. So this node will want to figure out exactly which transaction or transactions are at the root of this discrepancy. How exactly can that happen? Well, one solution at this point is to iterate through each of the 1 million transactions and then compare the sender, the recipient, and the transaction amounts to see where exactly the mismatch is. You'll realize instantly that this is a very, very inefficient method. And the longer the ledger, the more time it will take to find this mismatch on average. So while calculating the hash of the entire ledger and then frequently exchanging them to ensure that they're all consistent, does offer one way to ensure the integrity of the data. It does become very inefficient when there is some mismatch and you need to find out exactly what the root cause of that mismatch is. In addition, computing the hash of the entire ledger itself can use up a lot of resources if the ledger happens to be very large. So how exactly can we improve this situation? Well, one option is to break up a very large ledger into a number of blocks. So in our example, the 1 million transactions in the ledger can be broken up into 1000 blocks, with each of them containing 1000 transactions. So this is a view of one of the node's ledgers where we have 1000 blocks, and there is a hash which has been calculated for each of those 1000 blocks. So what we end up with now is essentially a blockchain or a chain of blocks. In order to ensure the consistency of this blockchain, the nodes can compare the hash value for each of the blocks. And while this is indeed a large number of hashes to compare, such a thorough comparison need not happen all the time, and you can only compare the hashes of the most recent blocks on a regular basis. This is especially true in the case of a blockchain, since the hash of any block is very much dependent on the contents of the previous blocks. So if all of the nodes in a blockchain network are in agreement about the hash of a block number n, then they are essentially in agreement of the entire blockchain until block n. What happens now though, if we were to find a discrepancy in the hashes of one of the blocks? Well, in that case, we only have 1000 transactions which need to be compared, as opposed to the 1 million transactions which we saw previously. So in order to answer the question which we posed at the beginning of this video of why exactly is data stored as a chain of blocks in a blockchain? Well, the answer to that is dividing a ledger into blocks is just a way to simplify the process of keeping the ledger consistent. Finding an inconsistency in one block is a lot easier than finding the source of a mismatch in an entire ledger, especially if the ledger happens to be very, very large. And the process can be made more efficient if we chain the blocks together by means of a cryptographic hash of the previous block, since this ensures that the hash of one block is dependent of all of the previous blocks in the chain. So if all of the nodes in the network have the same hash value for a particular block, it means that they will have the exact same contents for that block as well as all of the previous blocks in the chain. So dividing all your records into a series of blocks which are chained together is not only a great way to ensure the integrity of your data, but is also a very efficient way to ensure its consistency. And this is why such a data structure is called a blockchain, where you essentially have your data arranged as a chain of blocks. So far in this learning path, we have covered exactly what a blockchain is and how the integrity of a blockchain is ensured by means of including a cryptographic hash of the previous block within each block which is added to the blockchain. The purpose for including such cryptographic hashes is to ensure the integrity of transaction data, and there are multiple ways in which transaction data can be recorded on a blockchain. One of these is by means of smart contracts, and in this video we will cover exactly what those are and what their use cases are as well. So what is a smart contract? Well, a very simple definition is that it is a protocol to digitally specify, verify, or even potentially enforce the terms of a contract. While this may seem a little abstract, things will become clearer as we move along in this course. But for now, it is enough to think that a smart contract is pretty much the same as a traditional contract, with the primary difference between the two being that smart contracts are digital. That is, they're written using a high-level programming language, while traditional contracts are written using legal terms. So what exactly does this translate to, and what are the benefits of smart contracts? For that, we can take a look at an example of a business which wishes to raise funds for some venture. Let's just say for the launch of a new product. For this, it has set a target fundraising amount and also a deadline by which those funds need to be raised. This business has decided that the best way for it to receive these funds is not through investors, but by simply crowdsourcing contributions from a large number of supporters. Now, there are a number of crowdfunding platforms available which will allow such an interaction, but the mechanism is pretty much the same. That is, once a supporter makes a contribution towards a particular venture, those funds will be held in an escrow until a specific set of conditions are met. One scenario is when the target fundraising amount has been met before the specified deadline. When this happens, all of the funds which have been contributed by all of the supporters will be transferred over to the venture. That business then has the money it requires in order to go ahead with its product launch, and the contributors are also happy that they were able to support their cause in some manner. We can now take a look at another possible outcome where the target date has passed but the required funds have not been raised. In such an instance, all of the funds which have been gathered until that point needs to be refunded to the original contributors. So if such a scenario were to be implemented in real life, you will need both the supporters as well as the business which wishes to raise funds to register with some kind of crowdfunding platform. That platform will register each of these entities by making them sign some kind of terms and conditions, which in essence are simply contracts. By signing on to the contracts, each of the participants promises to behave in a certain manner in order to make this crowdfunding happen. The signing of the contract, however, does not automatically enforce that each person sticks to their end of the bargain. And this is precisely where smart contracts can come into the picture. So in the example which we just described, we have a collection of supporters, and all of these supporters will make contributions to a venture by going through some third-party crowdfunding platform. for example, Kickstarter. This platform will then ensure that all of the funds will make their way to the project team which has put up that venture on Kickstarter. To summarize this entire interaction, Kickstarter is a fundraising platform, and this will sit as a third-party entity which is trusted by both the project team as well as the prospective supporters of that project. In order to raise funds for a venture, a project team or a business will go over to Kickstarter and then create a new project there where they will describe exactly what they need the funds for, how much money they need to raise, and by what date. Once this has been done and the project has been successfully funded by the supporters, then the business which set up that project will fully expect that Kickstarter will hand over the raised funds to them. In fact, even the supporters will want to make sure that any contributions which they have made will go towards the project which they wish to fund and not towards any other cause. So the business as well as the supporters are expecting certain behavior out of Kickstarter. And this is in fact one major limitation of this entire interaction, that the supporters as well as the business need to place their trust in a third party. Now imagine that there may be many different fundraising platforms and not everyone will be trustworthy. Even though they may claim in the terms and conditions which the supporters and businesses sign on to that they will transfer over raised funds, some platform may decide to violate those terms, in which case it is up to the supporters and the business to take the matter up in court. Relying on lawyers and a judicial system to enforce the terms of a contract is not always the best option. So let us see what will happen if you were to alter this interaction in one significant manner. So the supporters, rather than making their contributions towards a trusted third party, which in turn will pass on the funds to the venture, what if they were to make their contributions towards a smart contract, which in turn will hand over the funds to the project team? We will explore this interaction in more detail in the next video. We saw in the previous video that if a business wishes to raise funds for a particular venture, they can make use of a smart contract rather than putting up their project on a crowdfunding platform. For this to happen, the smart contract needs to be coded in such a way that it holds all of the received funds until the specific goal is reached. That is, a fundraising goal has been reached before the deadline. In this case, the supporters of the project will transfer over their contributions towards the smart contract, which will effectively function as an escrow. If the project is a success, that is, the fundraising target has been reached before the deadline, then the smart contract will pass over the money it holds over to the product team. And on the other hand, if the project were to fail, then the money is automatically refunded back to the original supporters. Now, one very important way in which this interaction with smart contracts differs from having a trusted third party is that smart contracts are stored in a blockchain network. And since we have multiple nodes taking part in a blockchain network, the responsibility of enforcing the contractual terms is distributed, and there is no single entity which is in control of the contract or the money which has been contributed towards it by the supporters. An important thing to keep in mind about smart contracts is that these are written in code rather than in legal terms, which means that they can be executed. And in order to understand exactly what a smart contract represents, you will need programmers to interpret that, which contrasts with the fact that lawyers are required to interpret the terms of traditional contracts. Since smart contracts can be executed, they can effectively ensure the enforcement of the contract clauses by being run. So if the smart contract in our example promises to transfer over funds to the business once the fundraising target has been met before the specified date, then it simply needs to be executed to ensure that the transfer does indeed take place as stipulated. And the execution of a smart contract is something which is collectively managed by a blockchain network rather than by individual entities. And as a consequence, you don't need expensive lawyers or a judicial system to enforce the terms of the contract. It is the blockchain network which will manage that for you. Which brings us to the two crucial properties of smart contracts. The first one being that smart contracts are immutable, and the second one being that the responsibility to execute smart contracts is distributed across multiple nodes in a blockchain network. Focusing now on the first of these properties. So, the immutability of smart contracts means that once a contract has been defined, it can never be changed again. This ensures that no one can tamper with smart contracts, and if you do need to make a modification to an existing smart contract, you can copy its code, make the changes, and then deploy it as a brand new contract. The original contract will remain exactly as it is. Which takes us now to the distributed nature of smart contracts. This means that the output of the smart contract is validated by many nodes which participate in the blockchain network. This means, for example, that a single node or single person is not in a position to force the smart contract to release the funds. They will need to achieve a consensus among all of the nodes in the network. So just as with all of the records which are stored in a blockchain, you can also trust that a smart contract will behave exactly as it is defined. Nobody can alter its behavior since it cannot be modified, and no one can violate its terms because its output needs to be verified by the other participating nodes in the network. Which brings us now to a comparison between traditional contracts and smart contracts. We know that traditional contracts are defined in legal terms, whereas smart contracts are defined in code, usually in some high-level programming language. In the case of Hyperledger Fabric, for example, there are a number of general-purpose languages which can be used to define smart contracts, such as JavaScript and Go, whereas Ethereum, which is another blockchain implementation, has its own domain-specific language for smart contracts, which is called Solidity. Another point of contrast between traditional and smart contracts is that the legal terms in traditional contracts need to be interpreted by lawyers. But since smart contracts are written in some coding language, its terms need to be interpreted by developers. So while smart contracts can help you minimize or even eliminate the involvement of third parties in many interactions, they don't necessarily do away with the requirement for trained professionals to interpret and potentially write up the terms of a contract. Another important point of distinction between these two types of contracts is that traditional contracts may include some legal gray areas. In such a case, the actual interpretation of the contract may need to be handled by some arbiter or a judge. This contrasts, of course, with smart contracts, which happen to be written in code, which means that there is no ambiguity around its behavior. Everything is very much black and white. Which brings us now to the enforcement of contracts. And we have seen that it is the judicial system which enforces compliance in the case of traditional contracts. While a party may have signed on to the terms of a contract, that doesn't ensure that they will behave exactly as they have promised to. It will be up to the judicial system, with the threat of a fine or even jail time, to enforce that the party does act according to the terms of the contract. This is, of course, not the case with smart contracts, where it is the blockchain network as a whole which enforces compliance. This is something which can be done by simply executing the smart contract and then having all of the nodes which participate in the blockchain network verify its results and then write it to the blockchain. Which brings us to the last point of comparison, where a traditional contract may be either private or public. You could have copies of the contract which are only available to the signatories and not to anybody else. But such a contract may also be put up publicly for all to see. And in fact, this is also the case with smart contracts. And depending on the blockchain implementation, the smart contracts could either be entirely public or could also be private and held only by those participants who have signed on to the smart contract. In this exercise, you will first contrast centralized and decentralized ledgers. At the heart of it, blockchains store an ordered list of records, which means that they happen to be ledgers. When a number of different parties need access to a ledger, then there are two different ways to implement them, either as a centralized ledger which everyone can access, or a decentralized ledger where multiple parties maintain a copy of it. You will recall the characteristics, which include the benefits as well as the drawbacks of each of these approaches. Next, you will list down the properties of an ideal cryptographic hash function. During the course, we cover that blockchains make significant use of cryptographic hashing in order to ensure that the details which are stored on the blockchain cannot be tampered with. Since this technique is something which is used quite often, there are certain properties which you will require of a cryptographic hash function, and you will need to recollect what exactly those are. And for the final task in the exercise, you will compare smart contracts as they are implemented in many blockchain solutions with traditional contracts. We have covered during the course how smart contracts can potentially minimize or even do away with the involvement of a trusted third party in many different interactions. This, however, is accomplished due to certain characteristics of smart contracts, and you'll need to list down what they are and how those compare with traditional contracts. Each of these topics were discussed during this course, so please pause this video and then take some time to do this exercise on your own. For the first task in the exercise, you needed to distinguish between a centralized ledger and a decentralized one. We start off by looking at the implementation of these ledgers. In the case of a centralized ledger, it is rather simple because you only need to set up the ledger on a single host, and all of those who need access to it will just connect to it and retrieve the data. In the case of a decentralized ledger, however, because there are multiple nodes which need to be set up with it, this is going to be a little more complicated, especially given that you also need those nodes to be able to communicate with each other. Moving along now to fault tolerance. With a centralized ledger, there is pretty much no such thing. If the node holding the ledger were to go down, then all of those who wish to access the information on the ledger have no option but to wait until that host is brought back up. With a decentralized ledger, however, since there are multiple copies of that ledger floating around, even if one or a handful of the hosts having a copy of the ledger were to fail, the data will still be accessible. And moving along to access latency, if you happen to be located far away from where the centralized ledger is stored, then latency is going to be rather high. When a decentralized ledger is implemented properly, then the multiple copies of the ledger will be geographically dispersed, and anybody needing access to the ledger data only needs to send in a query to the host which is closest to them and has a copy of that ledger. And when it comes to updates to the ledger, centralized ledgers have only one copy, which is why these updates will be very quick. In the case of a decentralized ledger, on the other hand, this is going to be a much slower process since each and every copy will need to be updated. A side effect of this is that while updates are taking place on each copy of the decentralized ledger, some of those copies may contain stale data. This, however, is clearly not an issue with a centralized ledger approach. For the next task, you needed to note down the properties of an ideal cryptographic hash function. We saw in the course that each block of a blockchain maintains a link to the previous block by means of a cryptographic hash of the entire contents of that previous block. And because a cryptographic hash needs to be computed each time a new block is added to the blockchain, executing the cryptographic hash function should be rather simple and should not use up too many resources, whether in terms of compute resources or time. Another property is that a cryptographic hash should have a low likelihood of producing hash collisions. We have seen that the output of a cryptographic hash function such as SHA-256 can become very different if the input is even tweaked just a little bit. The effect of this property is something which feeds into the next desirable property of a cryptographic hash, which is that it should be impossible to recreate the original input message from just looking at the hash output. It is this property of a cryptographic hash function which ensures that a blockchain is immutable as well as verifiable, since one cannot reverse engineer the input message based on what they see as the hash output. Moving on now to the final task in the exercise, where you needed to distinguish between traditional and smart contracts. So first of all, in terms of the definition of these contracts, traditional contracts are defined using legal terms. On the other hand, smart contracts are written in code, usually in some high-level programming language. In the Hyperledger Fabric network, for example, you can write your smart contracts in either Node.js or Golang, whereas the Ethereum network has its own domain-specific language for smart contracts. The way these contracts are defined also determines who is able to interpret them. So in the case of the traditional contracts which are written in legal terms, you do need a lawyer to decipher for you exactly what the contract represents. And in the case of smart contracts, a developer who understands the language they have been coded in will be required. In both cases, you do need a trained professional to interpret what exactly the contract means. The next point of distinction between the two is in terms of ambiguity. With traditional contracts, there could be several legal gray areas which needs to be sorted out by either an arbiter or a judge. This is not the case at all with smart contracts, and because they are written in code, everything is very much black and white. The last point of distinction is in terms of contract enforcement. If one of the signatories in a traditional contract were to violate its terms, then you will need to rely on the judicial system to enforce the terms of the contract. In the case of smart contracts, however, enforcing the terms of the contract only requires the execution of the contract code, and for that you can rely on the blockchain network as a whole. And it is for this reason that smart contracts have the effect of minimizing the reliance on a trusted third-party entity. Previously in this learning path, we have covered the fact that blockchains offer a very secure way to store transaction data. Interactions where multiple parties are involved, such as in a supply chain, can benefit greatly from blockchain technology because it allows multiple potentially untrusted parties to work together since they trust that the system will not allow any fraudulent behavior. We also saw the power of smart contracts, which allows you to minimize and potentially even eliminate the involvement of a trusted third party in many different interactions. So given blockchain offers such a powerful technology, what are the different blockchain implementations out in the market right now which people and institutions can use? This is precisely what we will be covering in this video. To start off, we can summarize the benefits of blockchain networks which make it such a useful technology. First of all, the responsibility for maintaining the blockchain or even executing smart contract code is not restricted to just a single entity or a handful of them, but it can be distributed among multiple nodes participating in a blockchain network. This ensures that any transactions which have been initialized in a blockchain network will be verified by multiple parties before being committed to the blockchain. And once that data has been committed to the blockchain, you can rest assured that it cannot be modified in any manner after that. This is because every single record which is written to the blockchain can be verified. And this immutability and verifiability of transactions in a blockchain is accomplished by means of cryptographic hashing. We also saw with the use of smart contracts that you can minimize third-party involvement or potentially eliminate it entirely from many different interactions. The enforcement of the clauses of a smart contract do not really require a judicial system. Since it only involves the execution of the contract code, you can rely on the blockchain network to handle that. Given all of these benefits, blockchain networks allow multiple parties who don't necessarily trust each other to work together with the assurance that the system will not tolerate any malicious behavior. And this is why the technology is gaining a lot of support from multiple organizations, which has nothing to do with the cryptocurrency hype which has been flooding the news about blockchains. So an organization which wishes to use the power of blockchains might ask, what are the different types of blockchain networks available for us? If we wanted to conduct transactions in a secure manner with potentially untrusted partners, what system could we use? Well, there are a number of public blockchain networks available in the market. There is, of course, the Bitcoin network, which can be credited with bringing blockchain into the news and making the technology rather popular. And another widely used blockchain network, which is public, is the Ethereum network. Both of these are capable of storing transactions in a secure manner, and they also have their own cryptocurrencies. In addition to these properties, they also have several characteristics due to the fact that they are public blockchain networks. So what exactly are these? Well, for one, in a public blockchain network, anybody is free to join in as a node. There is no vetting process. As long as you have the required hardware and software, you can participate in maintaining the network as a node. A consequence of this low barrier to entry is that there are several nodes in a public blockchain network. Several thousand, in fact, in the case of Ethereum and Bitcoin. And another feature of a public network is that everyone can see the transactions which are recorded on the blockchain. And if the network supports smart contracts, those can also be accessible by all of the nodes. And just as with any blockchain network, there is a consensus mechanism. So all of the thousands of nodes can come to an agreement on what the contents of the transactions and the order of those transactions on the blockchain are. So given these, let us take a closer look at the consensus mechanisms in many public blockchains. As touched upon, the goal of the consensus algorithm is to get all of the nodes to agree on a valid state of the blockchain. And in addition to that, there also needs to be some way to punish fraudulent nodes. This needs to be done to ensure that all of the participants are behaving according to the rules of the system. An example of such a consensus algorithm is the proof of work algorithm, which is in use in the Bitcoin as well as Ethereum blockchain networks. So what exactly does this proof of work algorithm involve? Well, this is where all of the nodes which participate in the network enter into a competition to solve a complex mathematical puzzle. This puzzle is intentionally made very difficult, and once a node has solved it, it has effectively proven that it has performed a lot of work. And this is precisely where this consensus algorithm gets its name. The process of solving this puzzle is what is referred to as mining. So what exactly is the incentive for a node to solve this puzzle, given that it involves a lot of work? Well, the first node to find the solution gets a couple of privileges. First of all, they get to write the next block of transactions to the blockchain. And in addition to that, all of the fees associated with those transactions will also be credited to the node as mining rewards. So there are incentives for someone to enter as a mining node in the Bitcoin or Ethereum networks which use this proof of work algorithm. Though the odds of solving this complex mathematical puzzle before all of the other nodes in the network is very low for any single round. The expectation is that if you enter multiple nodes into the network, then over a long period of time, you will win enough rounds and collect enough mining rewards to make it worth your while to enter this competition in the first place. Whatever the case though, just entering this competition does involve expending a lot of resources in terms of compute power as well as electricity. And though I won't get into the specifics, the only way to solve this mathematical puzzle is by means of trial and error. And this is also a reason why any node can reasonably expect to be the first to solve this puzzle, at least on a few occasions over a long period of time. So while this explains the incentive for a node to participate in a public blockchain network, which uses the proof of work algorithm, what is the incentive for the nodes to behave according to the rules of the system? That is, not to enter fraudulent transactions onto the blockchain. Well, for that, let us see how exactly a node is able to collect a reward if it happens to be the first to solve the mathematical puzzle. Do keep in mind that until this point, this node has probably entered multiple rounds of solving this mathematical puzzle and has expended a lot of energy while doing so, all to no avail. But on this round, it has the opportunity to make up for all of that work put in previously by collecting the mining rewards. So how exactly can it collect the rewards? Well, once this node has staked its claim, that claim needs to be verified by all of the other nodes in the blockchain network. And one step in this verification involves verifying each and every transaction which that node wishes to add to the blockchain. If even one of those transactions is not verified, then that node's claim is rejected. And it also means that the node has wasted a lot of resources in trying to solve the mathematical puzzle, and when it got the opportunity to collect rewards, its claim was rejected due to a fraudulent transaction. So this proof of work consensus mechanism is something which ensures that all of the participating nodes in the network are behaving according to the rules. This does come with a caveat, however. A node's claim is considered verified if more than 50% of the participating nodes in the network consider that to be the case. So this system works as long as more than 50% of the nodes in the system are not compromised. In the previous video, we were introduced to a couple of the public blockchain networks available, namely Bitcoin and Ethereum. We also saw how those networks ensure consensus among the participating nodes by means of the proof of work algorithm, which incentivizes nodes to participate in the network and also punishes those nodes which try to enter fraudulent transactions onto the blockchain. Let us now take a closer look at some of the properties of the two blockchain networks we have discussed. Starting with the Bitcoin network. Many different organizations would like to make use of blockchains in order to perform transactions in a secure manner. However, the Bitcoin network is not quite suited for this task because it only supports one form of transaction, and this is the transfer of its cryptocurrency, which is also called Bitcoin, from one account to another. This lack of flexibility in the Bitcoin network is due to the fact that it does not support smart contracts. It is smart contracts which allow users to specify their own transactions which need to be recorded on the blockchain. And the lack of this feature means that the Bitcoin network is rather limited in its scope. Which takes us along now to the other public blockchain network which we discussed, which is Ethereum. So this is the most mature of the public blockchain networks out there. And this explains why Ethereum is among the most widely used of the public blockchain networks. One of its crucial features, of course, is the support for smart contracts, which can be coded in its own domain-specific language known as Solidity. The example which we described earlier on in this learning path about a trusted third party for fundraising is something which can very much be implemented by means of Ethereum smart contracts. Consensus on Ethereum is achieved by means of the proof of work algorithm, which means that the mining rewards need to be paid up using its cryptocurrency, which is known as Ether. This cryptocurrency is readily available, however, because it is publicly traded just like any other regular currency. At the time of this recording, for example, one Ether can be purchased for about 160 US dollars. So with the use of blockchain technology and the support for smart contracts, it may seem as though Ethereum is an ideal solution for some of the problems we have discussed, such as recording transactions on a supply chain and also working as a crowdfunding platform. While all of this can be done using Ethereum, there are, however, several limitations. So this brings us to the concerns around the Ethereum network, which has prompted other blockchain implementations to arise. So while Ethereum can be relied upon to record transactions in a secure manner, it cannot really do so on a very large scale. For instance, at the time of this recording, the Ethereum network is only capable of processing a few hundred transactions a minute. This is clearly not adequate for many large organizations such as banks or the credit card companies, let alone the fact that there is just a single Ethereum network for use by all entities in the world. So this factor alone is a deal breaker for many different organizations, but there are additional limitations with Ethereum as well. One of these is to do with the utilization of resources, and we have seen that the proof of work algorithm does a good job to ensure that the participants stick to the rules of the network and prevents malicious entities from getting involved. This security, however, comes at a rather high price. And you may have read in the news about the amount of electricity which is consumed by the Bitcoin network alone, which also uses the proof of work algorithm. And in addition to the scaling and resource usage concerns, there are also issues with confidentiality. Since Ethereum happens to be a public blockchain network, it means that all of the transactions are available for everyone to view. The details of the transaction include the originator account, the recipient account, as well as the value of Ether which is transferred, if there is any at all. So the account numbers themselves don't necessarily give away the identity of the individuals controlling those accounts. But if some friend of yours, say, were to transfer some Ether over to you, you will have access to their account number, and then you will be able to view all of their past transactions recorded on the Ethereum network using that number. So confidentiality of transactions is definitely a weak point of the Ethereum network, and though it is still not a problem for many different use cases, there are several situations where this alone is very much a deal breaker. So these are the three significant problems around the Ethereum network which cannot readily be fixed. And this is precisely where Hyperledger comes into the picture. The aim of Hyperledger is to come up with blockchain networks which have all of the positive characteristics of Ethereum, such as the ability to securely record transactions on a blockchain and then define your own transactions using smart contracts, but without all of the problems associated with that network, which revolve around scaling, resource usage, as well as confidentiality. In the next videos, we will take a look at exactly how Hyperledger achieves these goals. In the previous video, we took a look at some of the benefits of using the Ethereum network to record transactions, and also saw that it is not ideally suited for many different use cases. It is these concerns around Ethereum and a number of the other publicly available blockchain networks which has prompted the development of the Hyperledger project. In this video, we will take a look at what the goals of the Hyperledger project are and the ways in which they wish to achieve those aims. So leaving aside all of the hype, we have seen that blockchain networks offer several different features and benefits. The fact that these networks are distributed across multiple nodes makes sure that there is no single entity which is in charge at any given point in time. Transactions once recorded on the blockchain are immutable, and they are also verifiable. Both of these are crucial security features. And by means of smart contracts, we also have the ability to minimize or entirely do away with third-party involvement for many interactions. There are many implementations of blockchains available in the market, and one of the most popular ones is the Ethereum network. While Ethereum offers all of the benefits of blockchains and is publicly available, there are several issues around scaling, resource utilization, and confidentiality. We can now zoom in on each of these individual concerns in a little more detail, starting with the issues around scaling. We have discussed that there are only a few hundred transactions which Ethereum is capable of processing every minute, and this translates to about 3 million transactions every day. While this may seem like a rather large number, this is clearly not enough for many different enterprises, especially banks and credit card companies, which deal with several million transactions a day. And when you consider the fact that there is just a single main Ethereum network, which is available for the entire world, 3 million transactions a day for 7 billion people is clearly not enough. And while Ethereum can make incremental improvements to the number of transactions processed, being able to handle the load for even a single large organization will require an improvement in orders of magnitude. And the main reasons why Ethereum is unable to scale beyond this point is that the verification of the transaction, as well as the proof of work verification, does take up a lot of time. So the consensus mechanism in Ethereum will need to be revamped significantly in order to improve the throughput of the network. And to be fair, the Ethereum developers are very much working on this, though it is proving rather difficult to implement a new consensus algorithm. Which takes us now to the other big concern around Ethereum, which is to do with resource usage. We have seen that the proof of work algorithm involves all of the participating nodes entering into a competition which involves solving a complex mathematical puzzle. This is done for each new block which needs to be added to the blockchain, and the winner of that competition earns the privilege of writing the new block. However, all of the other nodes will have performed a lot of work to find the solution, but their effort will have gone to waste. This approach, of course, does involve the use of massive amounts of electricity, almost to an absurd extent. For example, there are several companies which have set up server farms in countries such as Iceland, where the cooling costs are low and electricity is rather cheap. And the machines in those farms will work as mining nodes in the Ethereum or Bitcoin networks. So while the proof of work algorithm does impede malicious behavior on the network, it does come at a massive cost. And while there are several alternatives to proof of work which have been discussed, these are far from being silver bullets. The proof of stake algorithm, which is currently being considered for Ethereum, is one which is likely to favor those organizations which are capable of putting up a lot of money and rules out a lot of small players. And this alone may not help achieve the necessary scale to make Ethereum a usable solution for many entities. Which takes us now to the security concerns around Ethereum. So the issue which we have discussed is that anybody is able to view the details of transactions which are recorded in Ethereum. The same also applies to other information such as the ether balance of smart contracts, for example. While you may want some information to be available publicly, there may be other details which you wish to keep confidential. And this lack of a mechanism to regulate access to data on Ethereum is one of its crucial drawbacks. Another issue, which we have only briefly alluded to, is the fact that it is possible for a fraudulent entity to control the network. This is not yet an immediate concern, but with some of the public blockchain networks, there are just a handful of entities which control the vast majority of nodes which make up the blockchain network. If these entities were to get together, then it is possible for them to effectively take over the network and then issue and verify their own fraudulent transactions. So it is these concerns around scaling, resource utilization, and security and confidentiality which has prevented the widespread adoption of Ethereum and other public blockchain networks. And it is to address these concerns that the Hyperledger project has been set up. So the goal of Hyperledger is not to provide a single blockchain network which is similar to Ethereum. In fact, the idea is to come up with a number of different frameworks. And all of these frameworks must fulfill certain characteristics. First of all, they must be suitable for use in an enterprise, which means that they should not have the issues around scaling, resource utilization, and security, which we have discussed. The solutions must also be open source, and this is to enable widespread adoption of blockchain technologies. Of course, the solutions must also be robust and immune from hacking so that people can trust the solution. And since the idea is to come up with multiple solutions rather than a single one-size-fits-all one, the solutions can be industry specific. So for example, you can have one blockchain framework for supply chain management, another one for financial transactions, and so on. So given these are the goals of the Hyperledger project, let us take a look at some of its properties. So as mentioned, Hyperledger is not a single blockchain solution, but is in fact an umbrella of open source blockchain implementations. So you have multiple solutions available, each of which could be industry specific. The Hyperledger project was founded in 2015, so by now, considerable research has gone into these solutions. This is something which is maintained by the Linux Foundation, which means that all of their open source experience has been employed in developing the solutions in the Hyperledger project. Another important thing to keep in mind is that it's not just the Linux Foundation which is working on its own, but that the Hyperledger project is a collaborative one which involves several industry leaders as well. So the goal is very much to find a solution which works for a number of different industries. And this is something which is reflected in the membership of the Hyperledger project, where you have organizations from the world of tech, finance, automobiles, and many other fields which are represented. And of course, the involvement of these different industries means that it is possible to come up with many industry-specific solutions. We saw in the previous video that the goals of the Hyperledger project was to come up with not a single one-size-fits-all solution for blockchains, but to come up with various solutions which may be suited to specific industries. We will now take a look at some of those blockchain implementations which have been developed by Hyperledger, and also some of the accompanying tools which make it easier for us to work with those networks. So the Hyperledger project can broadly be divided into two categories. The first of these is Hyperledger Frameworks. So these are enterprise-grade blockchain networks and are meant for a consortium of organizations. So for example, you have multiple companies involved in a supply chain, and they could all collaborate to set up a blockchain network using one of the available Hyperledger frameworks. Now, setting up, configuring, and maintaining blockchain networks can be a rather painstaking task, which brings us to the other category of projects under the Hyperledger umbrella, and these are known as Hyperledger Tools. These are specialized software which are meant for designing, deploying, and maintaining blockchains and blockchain networks. They abstract away a lot of the underlying complexity around setting up and maintaining of blockchains and have the effect of democratizing blockchains so that it's not just technical people who are involved in its creation and maintenance. From these though, let us now begin focusing on Hyperledger frameworks. At the heart of it, you can consider that a Hyperledger framework is pretty much a blockchain network. Each Hyperledger framework is its own blockchain network with its very own characteristics, but in each case, there is an append-only distributed ledger which is involved, which makes up the blockchain, and each of the frameworks has its own consensus algorithm. Some of the frameworks are designed in such a way that the consensus mechanism is a plug-and-play service. So you're not tied to a single consensus algorithm and can switch between them depending on your requirements. Another feature of many of the Hyperledger frameworks is that access to the blockchain is not unrestricted, but can be regulated by means of permissions. So while there may be multiple organizations which are involved in the overall blockchain network, there may be some parts of it which are only accessible to a handful of those entities. This is something which ensures the confidentiality of certain transactions. And finally, all of the Hyperledger frameworks support the concept of smart contracts. So these allow you to define exactly the kind of transactions which you would like to be recorded on the blockchain. Which brings us now to the different Hyperledger frameworks which are available for us to use. The most widely used of the Hyperledger frameworks is called Fabric, and this is the one which we will focus on a little later in this course. Another widely used one is called Eroha. There is also a framework known as Sawtooth, and these are the three most popular frameworks available so far. A couple of the other frameworks under the Hyperledger umbrella include Hyperledger Indie, and another one which is currently under development is known as Hyperledger Grid. So this clearly drives home the point that Hyperledger does not just involve a single blockchain network, but in fact, a wide variety of solutions are available. Let us now focus on some of these frameworks, starting with Hyperledger Fabric. Hyperledger Fabric offers a permissioned blockchain network, so it is possible for you to regulate who has access to which parts of the blockchain. This can be used to ensure confidentiality of certain transactions and other data. Fabric offers a lot of flexibility when it comes to the consensus mechanism as well as membership services. Membership services determine who exactly has access to the network. So Fabric is by no means a public blockchain network, but is very much a private one where you can control who exactly gets to participate. And since you can have multiple organizations on a Hyperledger Fabric network, each of those may have their own membership services. For example, they may each have their own trusted certificate authorities. Hyperledger Fabric can be set up to accept certificates issued by multiple CAs, and then those holding those valid certificates can participate in your network. Fabric has been implemented using the Go programming language, and it is also one of the accepted languages for developing Fabric smart contracts. Some other general purpose programming languages such as Java and Node.js can also be used for this purpose, which means that it's far easier for organizations to develop smart contracts for Hyperledger Fabric than, for example, with Ethereum, where you need to know a domain-specific language called Solidity. And finally, Hyperledger Fabric also happens to be the most mature and the most widely used of the frameworks available right now. So there is enough documentation available online for you to get started. And if you do run into any issues, there is enough information available online for you to tackle those and then move ahead with your work. We now take a look at another Hyperledger framework, which is Eroha. And this is something which has an emphasis on mobile application development. So the idea is to be very lightweight so that the blockchain network can be used from mobile phones. And to simplify this, Eroha includes a number of lightweight client libraries for both Android as well as iOS. And what simplifies this further is the fact that Eroha has been written using C++. Moving along now to Hyperledger Sawtooth. So this is a framework which has initially been contributed by Intel. It offers support for both permissioned as well as permissionless blockchains. One of the key features of Eroha is that it separates the application level from the underlying system. So it is possible for you to build applications for Hyperledger Eroha using high-level abstractions. Moving along now to Hyperledger Indie. So this is a framework which has been built around the concept of providing decentralized identity. This means that the details which make up your identity are not stored on a single entity, which could potentially be hacked and your identity compromised, but pieces of your identity may be stored across multiple entities which need to work together in a peer-to-peer fashion in order to establish who you are. This decentralized identity simplifies the process of developing solutions which span multiple industries. So if you happen to be involved in projects involving governments, educational institutions, and private enterprises, each of which have their own means of establishing identity, then Hyperledger Indy might be a solution for you to consider. Which moves us along to Hyperledger Grid, and this is a framework which has specifically been built with supply chain management in mind. This is why Hyperledger Grid provides data types, data models, as well as overall business logic which are specifically suited to the task of supply chain management. So while the specific characteristic of each individual framework may not matter to you, the big picture view which you must keep in mind is that the Hyperledger project does not offer just a single solution, but there are a variety of solutions for you to choose from depending on your own specific requirements. In the next video, we will take a look at the Hyperledger tools, which greatly simplify the use of these Hyperledger frameworks. In the previous video, we took a look at what Hyperledger frameworks are and covered some of the different frameworks which are currently available. We will now take a look at the tools which make it easier to work with those frameworks, and these are collectively known as the Hyperledger tools. We had discussed the fact that Hyperledger is in fact an umbrella of open source projects which can broadly be cast into two categories: Hyperledger frameworks, which are various implementations of blockchains, and Hyperledger tools, which are software meant to make it easier to work with those frameworks. We can now focus on the specific features which are offered by the Hyperledger tools. One of these is to allow us to implement blockchains by means of modeling rather than having to specify detailed configurations. For example, rather than worrying about individual blocks and accounts and nodes, if you could define the participants in the blockchain network and the types of operations which they need to perform, this is a much more intuitive way for us to work with blockchains. And these are exactly the features which are provided by some of the Hyperledger tools. Once the blockchain has been defined, in order for us to use it, we will need to deploy the blockchain and then following that maintain the network as well. And there are also a number of Hyperledger tools which make this process a lot easier. Once the data is in use, we can also use Hyperledger tools to view the contents of the ledger. This can be done using a simple user interface rather than having to dig through the file system of the hosts which are running the blockchain network. And since one of the goals of the Hyperledger project was to create enterprise-grade blockchain systems which are able to process transactions at scale, it also becomes essential to measure the performance of our Hyperledger frameworks. So you don't need to make use of some third-party tools or build your own process in order to measure performance. You can simply use one of the Hyperledger tools to do that. So what are the different Hyperledger tools available? Well, one very commonly used one is called Hyperledger Composer, and this allows you to provision a blockchain network by specifying high-level business abstractions. This includes its own modeling language, which you can use to define participants, assets, as well as the type of transactions which will be included in your blockchain network. Then there is Hyperledger Cello, whose goal is to provide blockchain as a service. You can use a simple user interface in order to define the type of network which you want, and then deploy this across a number of hosts which you have connected to Cello. Then in order for you to be able to view the contents of your blockchain network by means of a user-friendly web application, there is Hyperledger Explorer. You can use this web application to view details such as transactions, blocks, and smart contracts which have been deployed to your blockchain network. A tool which, as of this recording, is still in the incubation phase is Hyperledger Caliper, and this is the one you can use in order to measure the performance of your blockchain implementation. This allows you to calculate various metrics for your blockchain network, such as the transactions processed per second, transaction latency, resource utilization, and so on. And another tool which is still in incubation is Hyperledger Quilt. This is something which is meant to offer interoperability between different ledger systems. and some of these may even be outside of Hyperledger. We can now take a look at a few of these in detail, starting with Hyperledger Composer. As mentioned, the purpose of using Hyperledger Composer is to allow you to specify your business networks by means of a modeling language. Composer includes several business-level abstractions, and as a result, this truly democratizes blockchain technology, since you don't just need technical people involved in setting up a network. And while building your network, you may also choose to use one of the several templates which are included as part of Hyperledger Composer. And to make this tool truly accessible, it is available as a web UI. So you can provision, configure, and then deploy your blockchain network without ever having to use the command line. Moving along now to Hyperledger Cello. As mentioned, this is meant to provide blockchain as a service. Much like Composer, Cello also comes with a web UI, and you can use that in order to provision your blockchain network and then deploy it across a number of different hosts. The overarching goal of Hyperledger Cello, however, is to simplify blockchain lifecycle management. So the idea is to simplify the process of building your blockchain network, testing it out, deploying it, and then once you don't have any use for it, you can also use its UI to destroy your blockchain network. Which takes us now to Hyperledger Explorer, which is once again a web application. It includes a UI which allows you to explore details of your blockchain network, including the blocks, transactions, the nodes which are participating in the network, and so on. Hyperledger Caliper is a blockchain benchmarking tool. The metrics which it supports in order to measure the performance of your blockchain network include transaction latency, the throughput of transactions, and also the overall efficiency of your network when it comes to resource utilization. And finally, Hyperledger Quilt is meant to offer interoperability between different ledger systems. And these ledgers need not even be based on a blockchain. For example, Quilt also supports the JavaScript interledger implementations. So with that, we now have an idea of what Hyperledger frameworks are and how tools can be used in order to make it easy for us to work with those frameworks. So now that we have an idea of the different projects under the Hyperledger umbrella, how exactly can we make use of it? So we have seen that Hyperledger includes a number of different frameworks, many of which are suited for a very specific use case. So you will need to do some amount of research on what the different features are in each of the frameworks, and then pick the one which suits your requirements. Your choice does not just end there, because many of the Hyperledger frameworks allow you to select some of the components which make up your blockchain network. For example, in Hyperledger Fabric, you have a few different consensus mechanisms to choose from, and you can also specify your own ordering service in some cases. Once you have made your selections and then provisioned your blockchain network, you will need to configure the permissions for the different users in your system. For example, some of the users may require that their transactions be kept confidential, and access should only be restricted to some of the participants in your entire network. And while all of this can be done manually by essentially running various commands from the command line, editing configuration files, and so on, your task can be made a lot simpler if you just choose the correct Hyperledger tools, which will simplify the whole process of building, using, and then maintaining your blockchain network. So this is Hyperledger in a nutshell. A choice of blockchain frameworks for you to choose from according to your requirements, and a set of tools to make the entire process of building and managing your blockchains a lot simpler. In this exercise, you will list down the characteristics of public blockchain networks. The different Hyperledger frameworks are all implemented as private blockchain networks, and this is because there are several properties of public networks which don't make them ideally suited for use by enterprises. You will need to identify those not so ideal properties of these public blockchain networks. For the next task, you will enumerate the limitations of the Ethereum network. While Ethereum is a very popular implementation of a blockchain network, which also includes the feature of smart contracts, there are several limitations which have prevented Ethereum from being adopted on an enterprise scale. You will need to recollect what the specific concerns around Ethereum are. And for the final task, you will need to describe the purpose of the Hyperledger Tools. We saw during this course that the Hyperledger project essentially consists of a number of different blockchain implementations which are known as Hyperledger Frameworks. And then along with those, there are also some Hyperledger tools. You will need to identify exactly what these tools are meant to be used for and what some of their characteristics are. And you could also go ahead and name some of the Hyperledger tools which are currently available. All of these topics were covered during this course, so please pause this video and then take some time to perform this exercise on your own. For the first task in the exercise, you needed to note down the characteristics of public blockchain networks. The word public in this case means that anybody is free to join the network. There is no real vetting process in order to become a member, and anyone who has the required hardware and the software to connect to the blockchain network will be able to participate as a node. This low barrier to entry means that public blockchain networks contain not just a handful, but several nodes. And the most popular public blockchain network contain tens of thousands of nodes. All of these nodes are treated in exactly the same way and have a similar role in the blockchain network. So there are typically no specialized nodes in a public network. Another consequence of a public blockchain is that the data which is recorded on the blockchain itself, that is the transaction data, happens to be public. The transaction data which is available for everyone to see includes the origin account, the sender account, as well as the value of any cryptocurrency which is being transferred. While there could be some additional data as well, these are the three most important fields. And what you'll notice here is that the account information is publicly available. However, the identities behind those accounts will not be visible. If you do happen to find someone's account address, however, it will be possible for you to view all of the transactions which have been initiated on the public blockchain network. So this is not the place for you to expect confidentiality. Now, when you have multiple, potentially thousands of nodes working together, there needs to be some mechanism for all these untrusted nodes to arrive at a consensus. This consensus mechanism must get the nodes to agree on what the valid state of the blockchain is, and in addition to that, it should also punish nodes for fraudulent behavior. This is something which is accomplished by means of the proof of work algorithm, which is the consensus mechanism being used in the most popular public blockchain networks at the moment, namely Ethereum and Bitcoin. For the next task, you needed to note down the limitations of the Ethereum blockchain network. So there are several reasons why Ethereum has not been adopted by enterprises, and this has to do with three main concerns. The first of these is the ability of Ethereum to scale. At the time of this recording, the Ethereum network is only able to process about 3 million transactions a day. Many large enterprises, such as banks or e-commerce platforms, may want to record tens of millions, if not hundreds of millions of transactions on a blockchain. And clearly, the Ethereum network is not capable of handling that at the moment. Another limitation of the Ethereum network is around resource utilization. So the proof of work algorithm does a rather good job of preventing fraudulent behavior on the network, but this comes at a rather high price. A lot of compute resources or time are expended in solving the proof of work puzzle, and of all the thousands of nodes which participate in this proof of work puzzle, only one gets to write the new block to the blockchain. Nodes end up incurring very high electricity costs as a result, and one could argue that this is mostly wasted effort, and there must be a more efficient way to ensure that there is no fraudulent behavior. Which takes us to the third main concern around Ethereum, which is to do with the confidentiality of data. As we have seen, on Ethereum, all of the transaction data is publicly available, and if someone is able to trace an account number to you, perhaps when you initiated a transaction with them, then they will be able to view all of your past transactions on the Ethereum network. This is simply unacceptable for many enterprises who will want some degree of confidentiality for many transactions. It is these concerns around scaling, resource usage, and confidentiality which have prevented many enterprises from making use of Ethereum. Which takes us now to the final task in the exercise, where you had to summarize the purpose and the properties of Hyperledger Tools. So the goal of the Hyperledger Tools is to make it easier for users to work with Hyperledger Frameworks. For example, rather than defining your blockchain network in terms of configuration files, running scripts, and so on, there is a tool called Hyperledger Composer, which allows you to define your blockchain network by means of modeling. Here you can make use of business-level abstractions to define the various assets in your blockchain network, the different participants, as well as the type of operations which are permitted. So while the users work with the high-level requirements, the nitty-gritty of the implementation is handled by Hyperledger Composer itself. The task of deploying and then maintaining blockchains is made far simpler by a tool such as Hyperledger Cello, which allows you to perform all of these tasks through a very nice web application. In order to view all of the data in your ledger, as well as to explore other details about your blockchain, a tool such as Hyperledger Explorer provides a rather intuitive UI, which saves you the trouble of navigating through file systems on multiple hosts to gather that same information. And a tool such as Hyperledger Caliper allows you to measure the performance of your blockchain network through various metrics, which include the throughput of the network, transaction latency, as well as overall resource utilization. Previously in this learning path, we have seen why blockchain is such a promising technology and why a number of different organizations are considering adopting it in some form. We also covered how Hyperledger provides a number of different blockchain solutions which you can choose from depending on your own requirements for blockchain technology. The implementations of blockchains which Hyperledger provides are collectively called Hyperledger Frameworks, and each framework has its own characteristics which may be suited for a specific purpose. The most widely used of the Hyperledger frameworks is one which is meant for general use and is not catered to specific industries. And this is Hyperledger Fabric, and it is going to be the focus of this course. Let us begin by taking a look at some of the benefits of using blockchain technology. Blockchains are distributed in nature since there is no single entity which maintains the blockchain. That is a collective responsibility of all the participants in a blockchain network. Also, once data has been written to a blockchain, it cannot be modified in any way, and the transactions which are recorded can also be verified. These are the characteristics which allow multiple parties who may not necessarily trust each other to work together in a blockchain network, since they know that what is recorded on a blockchain has not been tampered with by anyone. Also, if a blockchain network supports smart contracts, then you can use those in order to minimize the involvement of a trusted third party in many different interactions. So given all of these advantages of using a blockchain system to store data and record transactions, what are the different implementations of blockchains which are available for us to use? One of the most commonly used ones is the Ethereum network. So this is a decentralized open source and public blockchain-based platform, and this does include the feature of smart contracts. We can now delve into some of the characteristics of the Ethereum network. For one, it is a blockchain-based platform. So all of the transactions which are recorded in Ethereum are stored in a blockchain. Ethereum is an open source project, which means that its source code is maintained by a community of developers. They make frequent bug fixes, and there are also talks of changing the consensus mechanism which is in use currently on Ethereum. Any big news like that will be made available to the public so that users can plan accordingly. The fact that Ethereum is a public blockchain network means that anybody is free to join the network. There is no vetting process, and there are no real barriers to entry. All you need is the required hardware and software in order to participate as a node in the network. Since anybody can join this network, we must expect that there may be some malicious entities who may try to defraud the participants in the network, which is why Ethereum includes a mechanism in order to allow members to work with untrusted nodes. This is achieved by means of the proof of work consensus algorithm, which ensures that any node which attempts to break the rules of the network will be punished. Also, in order to execute the code of smart contracts, Ethereum uses something known as the Ethereum Virtual Machine or EVM. For those of you who have experience programming in Java, you can think of this as being similar to the Java virtual machine. With all of these features, it may seem as though Ethereum is the ideal solution for many different enterprises who wish to use blockchains in order to record their transactions. This, however, is far from happening, and this brings us to the concerns around Ethereum which has prevented its widespread adoption. The first of these has to do with the scale of operations on Ethereum. At the time of this recording, Ethereum is only capable of processing about 3 million transactions per day. This is far from adequate for many different enterprises, let alone the fact that Ethereum is just a single blockchain network available for the entire world. Given that large banks or credit card companies are used to processing tens of millions of transactions per day already, this is clearly not a solution for most enterprises. Another limitation of Ethereum has to do with the utilization of resources. The primary culprit here is the proof of work consensus algorithm, which does its job of preventing fraudulent behavior. However, this does come at a huge cost in terms of electricity consumption and the use of processing power. And given that the network is a public one, there are several issues around confidentiality. Ethereum has no means for users to regulate access to the network, and all transaction data is available for everybody to see. So all of these limitations have prevented Ethereum from being adopted on a much greater scale, and have also held back the adoption of blockchain technology in general. So clearly, Ethereum and many of the available blockchain implementations out there are not the ideal solution for enterprises. With that said, what exactly do enterprises want out of blockchain technology? What can be considered an enterprise-grade blockchain? Well, for one, an enterprise-grade blockchain network will have a high throughput. They should at least be able to process tens of millions of transactions per day, if not in the billions of transactions. For that to happen though, transaction processing itself must be an extremely efficient operation. Each transaction must be processed in mere fractions of a second. An additional factor is that transaction fees should be very limited or at least predictable. In the case of the Ethereum network, you effectively make a bid in terms of the transaction fees, and the higher your fee, the more likely your transaction is to be processed immediately. This is not ideal for many enterprises who may want the choice of either fixed or even zero transaction fees, which can simplify the task of planning their finances. Other considerations for enterprises include optimum resource utilization. If compute power is being utilized, it should ideally be devoted to processing of transactions rather than in an attempt to win a competition, which will allow you to potentially reap some rewards. In other words, the proof of work algorithm is a waste of resources. Additionally, enterprises will also want some degree of control over the nodes which are participating in the blockchain network. So rather than have a public network such as Ethereum, if there can be some vetting process to ensure that those who are participating in a network can be trusted to at least some degree, then this ties in with the resource utilization, since you don't need to waste a lot of resources to ensure that the participating nodes are behaving correctly. Another requirement is that it should not require the learning of a brand new language in order to develop smart contracts. If these contracts can be written in commonly used languages such as Node.js or Java, then enterprises will find it much easier to find the talent to write those smart contracts. And in addition, many enterprises will want the ability to configure the blockchain network rather than use a prepackaged solution without any configuration options. Some of the details which they would like to control include who has access to the system and what degree of access. They may also want some degree of control over the security settings in the blockchain network. This may include mechanisms to access the network and so on. And they may also want to set up their own membership services, which will regulate who has access to the network and how their identities are established. Companies may also wish to pick the consensus mechanism which is used in their blockchain network. So now that we have an idea of what an enterprise-grade blockchain network looks like, we can go ahead and take a look at how Hyperledger Fabric fulfills all of these requirements. That is something we will do in the next video. In the previous video, we saw what the requirements are for an enterprise-grade blockchain network. The goal of the Hyperledger project is not to provide a single blockchain network which fulfills those conditions, but to offer a variety of them, each with their own unique characteristics, which you can choose from in order to build your blockchain network. While these frameworks may have their own unique characteristics, let us take a look at some of the features which are common to all of them. So these Hyperledger frameworks are in essence blockchain networks, which means that each of them has an append-only distributed ledger. So you cannot modify the content which is already on the ledger. The only modification you can make is to add new records to it. All of the Hyperledger frameworks come with their own consensus algorithms. And depending on the framework, you don't necessarily need to stick with what is provided, and you can in fact plug in your own consensus mechanism. One of the requirements for enterprise-grade blockchains is to enable permissioned access to various parts of the blockchain network. And this is a feature which is supported by the Hyperledger frameworks. And a rather important feature is that these frameworks support smart contracts. So it is possible for you to define the types of transactions which you want recorded on your blockchain. We have covered previously in this learning path that there are several Hyperledger frameworks available, some of which have been specifically designed with one industry in mind. However, the focus of this course is on just one of those blockchain frameworks, which is Hyperledger Fabric. This is in fact the most mature and widely used of the Hyperledger frameworks, and one of the reasons for this is that it is a general purpose blockchain implementation and is not built for a specific industry. Fabric has been implemented in the Go programming language, which is why it also supports smart contracts which are written in Golang. The origins of Hyperledger Fabrics are in IBM, who provided the initial code for this network. However, it has been built upon considerably following that. Hyperledger Fabric is also a permissioned blockchain network, which means that it is possible for you to define various degrees of permissions for the different participants. And this is in fact an ideal solution to create private channels of communication among some of the participants in the network. For instance, you can ensure that specific transactions are only visible to some of the parties participating in the blockchain, and this ensures confidentiality of those transactions. Fabric also offers some degree of flexibility when it comes to the consensus mechanism. So this is a feature which is plug and play in Fabric, and there are a handful of options to choose from. This flexibility also extends to the membership services, and since different organizations might be using their own membership services, Fabric makes it a lot easier for them to jump on board this network. Since the organization only needs to register their membership service and don't need to create a new one in order to use the blockchain. Another important feature of Fabric is that it offers very high throughput, and this is partly due to the fact that it has streamlined the verification process, which is something we will explore just a little later in this course. One of the ways in which Fabric has achieved this high throughput is by eliminating the concept of mining new blocks, which means more of the network's compute resources can be used for transaction processing rather than for mining. And another feature which makes it easier for enterprises to jump on board is that Fabric does not really have the concept of a cryptocurrency or even transaction fees. This means that participants don't need to worry about the volatility of cryptocurrencies, and the lack of transaction fees is something which is made possible by the fact that those who participate in the network have been vetted to some degree and can be trusted to not invoke transactions needlessly. An important feature of Hyperledger Fabric is its support for smart contracts, which are often referred to as chain code. And crucially, you don't necessarily need to learn a brand new domain-specific language in order to code up these smart contracts, since Fabric supports multiple general-purpose languages. These include Golang, as touched upon previously, but also Node.js and Java. Companies should find it relatively easier to find programmers with these skills rather than those who need to learn a brand new language which is specific to just one blockchain implementation. This is something which contrasts Fabric with the Ethereum network. At this point, it is a good idea to compare both the Hyperledger Fabric and Ethereum networks just to emphasize why exactly Fabric is ideally suited for enterprises. First of all, Hyperledger Fabric is a permission blockchain platform, whereas Ethereum is permissionless. Fabric allows access to be regulated for users, and this translates to increased security and also confidentiality for transactions. Another feature which improves security in Fabric is that it is a private blockchain network, which means entry to this network is by invitation only. It is possible to have some kind of vetting process before someone is granted entry into the network, and this adds to its overall security and can also streamline transaction processing, since you don't need to take the extra precautions of having to work with completely untrusted nodes. This, of course, contrasts Fabric with the Ethereum network, which is a public blockchain network which anybody can enter. Fabric also has no associated cryptocurrency, which means that you don't need to go out into the currency markets before you can invoke transactions on Fabric. This is, of course, not the case with Ethereum, which uses a cryptocurrency called Ether. To invoke any transactions on the network, you need to pay a transaction fee, and this will be in the Ether currency. Another point of distinction between the two networks is that in Hyperledger Fabric, a transaction follows a life cycle of execute, order, and validate. Whereas this is a little different in the Ethereum network, where the transactions are first ordered and then executed. When it comes to processing transactions on Fabric, there is an explicit validation step, whereas in the case of Ethereum, the validation occurs as part of the execute step. On Fabric, transactions can be kept private as discussed previously, whereas in Ethereum, all the transactions are publicly viewable by not just the members of the Ethereum network, but by the general public. On Hyperledger Fabric, transactions can be processed at a much higher rate. That is, it has a rather high throughput, whereas with Ethereum, it can only process about 3 million transactions per day, which is very low for many enterprises. An important reason for the high throughput in Hyperledger Fabric is that the transactions can be executed in any order, even in parallel. This is because the ordering of the transactions occurs after the execution step. This is not the case with Ethereum, where the transactions are first ordered and then executed in exactly that order. This prevents the parallel processing of transactions and thus limits the overall throughput of Ethereum. Fabric also makes use of a separate ordering service in order to sort all of the transactions, whereas each of the mining nodes in the Ethereum network performs that transaction ordering before they execute those ordered transactions. In Hyperledger Fabric, you can have smart contracts which can do away with the requirement for a trusted third party in many interactions, and this is also the case with the Ethereum network. On Fabric, however, smart contracts can be coded in general purpose languages such as Golang or Node.js, whereas on Ethereum, this needs to be done in a domain-specific language called Solidity. So we have seen now that there are several concerns around the Ethereum network, around scaling, resource utilization, and confidentiality, but these have been mitigated in Hyperledger Fabric. We saw in the previous video that Hyperledger Fabric is able to generate a very high throughput. Much of this is due to the way transactions are processed in this blockchain implementation, and we will now be taking a closer look at this. So let us dive into transaction flow in Hyperledger Fabric. The flow of transactions can be categorized into three phases. The first of these is the execute phase, and this is where the code of the transactions is actually executed. Following that, the executed transactions are ordered, and performing the ordering of transactions after the execution allows the execution to take place in parallel. Once all of the transactions have been executed and ordered, they will need to be validated, and this is where each transaction is checked to see whether it fulfills certain conditions. This is, of course, a rather high-level overview, so we can now dive right in to exactly what this looks like. So this is the overall architecture diagram for transaction flow in Fabric. This all begins right at the top with a client application, which initiates a transaction in the Fabric network by creating something called a transaction proposal. You can see the various components which are involved in the transaction flow. There are endorsing peers, there is an ordering service, as well as a set of committing peers. We will now examine each of these components in detail, along with the messages which are passed between them. We will start off with the first of the three phases which we have discussed in the transaction flow, which is the execution of transactions. The two sets of participants in this process include the client application which initiates the transaction and a collection of endorsing peers which will execute those transactions. The process starts off with a transaction proposal which the client application will send, and this will contain the required information to execute the transactions. That execution will be handled by the endorsing peers, which may choose to endorse the transactions depending on certain conditions, which we will just take a look at. Do note that there are usually a number of different endorsing peers, and each of them will send back their own endorsed transaction back to the client application. We can now zoom in on the first phase of this execution process, which is the sending of the transaction proposal from the client app over to the endorsing peers. So what exactly is the information within this transaction proposal? As I mentioned earlier, this contains all the information which is required in order to execute a transaction. Since the code of a transaction will lie within a smart contract, this proposal will need to reference the contract from which the code needs to be executed. So this proposal will include, for example, some kind of identifier for the chain code or smart contract to be executed, the specific function within that chain code, as well as the arguments needed for that function. Each of the endorsing peers will have a copy of the chain code, and they can use the information provided in the transaction proposal to execute the required function and thus invoke the transaction. So while we have discussed a single transaction proposal here, in reality, there will be multiple client applications connected to the Hyperledger Fabric network, and many of these will submit transactions at a given point in time. So an endorsing peer will have received not one, but several transactions. So what does it do with these transactions? Well, given that the ordering of those will be decided at a later point in time, those transactions can just be executed, and this execution can happen in parallel. Once again, just to emphasize the difference between Hyperledger Fabric and Ethereum, for example, because the ordering happens after the execution of a transaction, parallel execution is possible, and this greatly increases the throughput of Hyperledger Fabric. So one thing about transactions on Fabric is that each of them needs to fulfill an endorsement policy. So what exactly is an endorsement policy? Well, a simple way to put it is that specific nodes in the Hyperledger Fabric network must agree on the results of the transaction execution. So these specific nodes will be among the endorsing peers, and an important thing to keep in mind is that not all of the nodes and not even all of the endorsing peers need to be involved in this process. For example, an endorsement policy could be something like peer number 1 and peer number 3 must endorse the transaction. So these are two specific nodes in the network which may contain many more overall. Another sample endorsement policy is that a majority of the peers must endorse the transaction. So in this case, it does not matter which specific nodes send in their endorsements, as long as there is a simple majority of all the nodes. An effect of having such a flexible endorsement policy is that not all of the nodes need to even see the transaction, and it is possible, for example, to have private transactions within the network. However, this endorsement policy does ensure that there is some kind of consensus among the relevant nodes in the system about what a valid transaction is. So with the transaction proposal and the endorsement policy, we now have an idea of what the first step in the transaction flow in Fabric looks like. Once the endorsing peers are done executing the transaction, and if they find that the results are valid, then they can send an endorsement of the transaction back to the client application. One thing to keep in mind is that the endorsing peers themselves will not be aware of the endorsement policy which the transaction must fulfill, and it is up to the client application to ensure that the transaction proposal reaches all of the relevant endorsing peers so that the endorsement policy can be fulfilled. Once the relevant endorsements are obtained, then the execution phase of the transaction flow has been completed. And just to summarize, this involves the client application sending a transaction proposal which contains all of the necessary information to execute the transaction over to a number of endorsing peers. It is up to the client to ensure that the transaction is sent to those peers whose endorsement is needed in order to fulfill the endorsement policy. The client will get back endorsed versions of the transactions back from the endorsement peers, and this concludes the execute phase of the transaction flow in Hyperledger Fabric. The next step at this point is to send over the endorsed transactions over to the ordering service. That is something we will take a closer look at in the next video. In the previous video, we were introduced to the overall transaction flow in Hyperledger Fabric, which goes through three different phases: execute, order, and validate. We took a look at the steps involved in the execution phase, at the end of which the client application which originated the transaction receives a collection of endorsements from a number of the endorsing peers. The transaction must receive enough endorsements to fulfill an endorsement policy, but once that is done, the client application can forward the endorsed transactions over to the ordering service. Which brings us now to the ordering phase of transaction flow in Fabric. So this is where the endorsed version of the transaction, which is the transaction along with All of the signatures of the endorsing peers is sent over to the ordering service. And exactly as the name implies, this is where the ordering of the transactions will take place. We'll be receiving endorsed transactions not just from one, but from multiple client applications which are connected to the Fabric network. It is up to the ordering service to gather all of these transactions and then sort them out. But what exactly is the technique which is used to sort these transactions? Well, there are three main ordering mechanisms available in Hyperledger Fabric. The simplest of these is called Solo, and this is what you will typically use in a dev setting. A production solution is Kafka, and this is usually the preferred option and is in fact the default option in Hyperledger Fabric. Another available choice for ordering is the Simplified Byzantine Fault Tolerance Mechanism, or SBFT for short. So Hyperledger Fabric is not tied to a single ordering service, and you can choose from the available options. You could also opt for one of these mechanisms in a dev or test setting, and another one for use in production. Let us take a closer look at each of these, starting with Solo. So this is where you have a single ordering node, which of course represents a single point of failure. While this is very useful to get you up and running with Hyperledger Fabric, this should ideally be used only for experimental purposes, like in a dev or potentially a test setting. These are environments where simplicity is a higher priority. However, Solo is not recommended for use in production, and you should use one of the other ordering mechanisms available for that. Which takes us along now to the Kafka ordering service. So this is by far the most mature and widely used of the ordering mechanisms in Hyperledger Fabric. And Kafka is in fact the recommended solution in production environments. This is because there is no single point of failure, and the Kafka ordering service is distributed across multiple nodes. As a result, it is highly fault tolerant, since your Fabric network can continue functioning if either one or even a handful of the ordering service nodes were to fail. Kafka also ensures that you have high throughput and low latency for your transactions. Kafka is a tool which is built and maintained by the Apache Software Foundation, and this is specifically meant for stream processing. This means that it can also be used for ordering events, which is exactly what is done in the Hyperledger Fabric setting. With that, we move along to the third ordering mechanism in Fabric, which is Simplified Byzantine Fault Tolerance. So this mechanism ensures two types of fault tolerance. One of these is the crash fault tolerance, where if even a handful of the ordering service nodes were to fail, then the system will continue to be up and running. However, another type of fault tolerance which is supported is Byzantine fault tolerance, which means that the system will continue to function properly even in the presence of some malicious nodes. The details of this mechanism is beyond the scope of this course, but it is enough for you to know that there are different ordering mechanisms which are available for Hyperledger Fabric, and you can choose which one to employ in your Fabric setting. Whatever your choice of ordering mechanism though, at the end of the ordering phase of your transaction flow, you will end up with a list of ordered transactions. And just to recap what we have at this point, in the first execute phase, the transactions were submitted and executed. The execution came along with certain endorsements, and now those endorsed transactions have been sorted into some order. Remember that in a blockchain, it is not just the content of the transactions which are important, but the overall ordering of the transactions as well. So now that we have endorsed and ordered transactions, we can move along to the next phase of transaction flow, which is to validate the results. This is the final phase after which a transaction may be committed to the blockchain. So what exactly goes on in the validate phase? Well, to start off with, the ordering service will send over its list of ordered transactions to one or more committing peers in the network. And we can zoom in on what the committing peers will do with those ordered transactions. So it is the job of the committing peers to validate the transactions and not to execute them. This means that they don't need to have a copy of the chain code. So what exactly do the committing peers do when it comes to validating transactions? Well, first of all, this validation process will occur in an order, so they will iterate through the list of ordered transactions and then perform the validation steps, which begin with checking that for each transaction, the endorsement policy has been fulfilled. One point to note here is that there is not a common endorsement policy for all transactions, but that each of them can have their own policies. So it is up to the committing peers to check what the endorsement policy of a transaction is, and then make sure that it has the required endorsements from the endorsing peers. Once the endorsement policy has been fulfilled, the committing peer will also need to check whether a particular transaction has been invalidated by a previous transaction. So this is where the ordering of the transactions comes into the picture. To understand what this might mean, consider two transactions. One of these is where account A transfers a certain value of money to account B. And then there is another transaction where account B transfers some money to account C. The ordering of these transactions can be important here because the account B may have started with no funds at all, and the transfer from B to C can take place only if the transfer from A to B took place before it. All in all, though, these are the main steps which are performed in the validation phase by the committing peers of the Hyperledger Fabric network. And once a transaction has cleared all of the validation steps, it can be committed to the blockchain. So we have now covered the transaction validation phase of transaction flow in Fabric. And just to summarize, a list of endorsed and ordered transactions is sent over from the ordering service over to the committing peers. The committing peers will iterate through the transactions in the order which they have received them in, and then will ensure mainly two things: that each transaction has fulfilled its endorsement policy, and that a transaction has not been invalidated by a previous transaction. Once a transaction has been validated, it will be written to the blockchain, and then as a final step, a transaction confirmation message will be sent over to the client application which originated the transaction in the first place. And with that, we have now concluded all of the phases of transaction flow in Hyperledger Fabric, starting from a transaction proposal to endorse transactions, to a collection of ordered and endorsed transactions, to finally a bunch of validated transactions which are written to the blockchain. And while this particular diagram does give you an idea of the various components involved in transaction flow, to understand where each of these may fit into the bigger picture, here is a Fabric architecture diagram. So we have three different organizations represented here, each of which have a number of peers. These could be either endorsing peers or committing peers, and each organization can have its own certificate authority to issue identities. What is common to all of these organizations, though, is the ordering service. So this is another way to look at all of the components which make up Hyperledger Fabric's network. In the previous video, when we covered transaction flow in Hyperledger Fabric, we covered the fact that a transaction has an associated endorsement policy. This endorsement policy means that the transaction needs to be endorsed by at least a handful of the nodes which make up the Fabric network. And those handful of nodes can be represented by means of a channel. That is going to be the focus of this video, where we take a look at what constitutes a channel in Fabric and what their purpose is. We begin by revisiting the example we have been working with during this learning path of a retail supply chain. Here we have 4 different participants in the supply chain, starting with a factory which manufactures some goods. Those goods are then sold on to a distributor, who in turn can sell off some or all of those goods to some wholesalers. It is now the turn of the wholesaler to sell off the goods to a retailer, who will then display the products on their shelves and then will finally sell it off to some customers. It is in the interest of all of these parties involved to record their transactions in a secure manner. This can help them keep track of where each of the products are in the supply chain and then plan accordingly, and can also be used in order to resolve any disputes which might arise with the delivery of products. And we have also covered the fact that an ideal way for these organizations to set up and record their transactions is by means of implementing a distributed ledger, such as a blockchain, and then collectively maintain that blockchain. And one of the blockchain implementations which they can consider using is Hyperledger Fabric. And we have seen in the previous video that this is an example of how a Hyperledger Fabric network can be set up. So here we are only considering 3 organizations, each of whom may have their own certificate authority to issue identities to their employees. They can also set up a number of peers which will make up part of the Hyperledger Fabric network, and these could be endorsing peers or committing peers. All of the organizations, though, will be making use of the same ordering service. So how could we fit this into our retail supply chain example? Well, consider that 3 of those organizations are represented here: the retailer, the factory, and the distributor. I have included only 3 of these organizations here for space considerations so that the slide does not look too cluttered. In reality, however, there will not only be the retailer, factory, distributor, and the wholesaler represented, but there could be multiple instances of each of them. For now, though, let us continue working with this simplified version of the Hyperledger Fabric network. So, out of these 3 organizations which maintain the network, consider that there is a deal between the 2 participants: the factory which manufactures the product and the distributor who buys the product from the factory. Both of these parties will negotiate a rate for the product, and then following that, the factory will sell the goods over to the distributor, and that transaction will be recorded on the blockchain. In such a situation, let us look at things from the point of view of the factory. So this factory will be supplying goods not just to a single distributor, but likely to many different ones. Now, some of these distributors may happen to get special rates for the same product. Now, there could be many different reasons for this. Perhaps these distributors have a long-standing relationship with the factory, and then the factory knows that once they supply the goods to that distributor, payments will be made on time, and that this distributor will come back for more business later on. So clearly, from the factory's point of view, all of the distributors cannot be treated on equal terms. And in such a case, it is in the best interest of this factory to have this deal with the distributor be confidential. If some distributors are getting a special rate, the factory will not want this to be known to all of the other distributors it supplies to. So a major requirement of the blockchain network for this factory is some confidentiality for its deals with the distributors, which translates to private transactions. So the details of the transactions which are recorded on the blockchain should be private to those participants who are involved in the transaction, and should not be available for everybody participating in the network to view. This is a requirement which has very much been taken into account by the creators of Hyperledger Fabric. So going back now to the Hyperledger Fabric architecture, we have represented 3 different organizations here: the retailer, the factory, and the distributor. Out of these, our focus now shifts to the 2 entities, the factory and the distributor, who have struck some kind of special deal and want the details of the transactions between them to be recorded on the blockchain, since it does offer a secure way to record this information. However, they want that transaction to be private to just both of them. So what they're really asking for is, in effect, a private channel of communication. And this is a feature which is supplied by Hyperledger Fabric, where you can have a channel which involves only some of the entities involved in the overall Fabric network, but allows them to make use of the common ordering service. You see here that this private channel connects 2 peers, one on the side of the factory and one on the side of the distributor, along with the common ordering service. This is a setup which does allow for confidential transactions. But how exactly does it work? So let us zoom in on what exactly a channel on Hyperledger Fabric entails. So the purpose of having channels is to enable the participating entities in the Fabric network to have confidential transactions. For those of you who have some background in networking, you can think of a channel in a Fabric network to be similar to a subnet. So it is one part of the entire blockchain network. An important implementation detail to keep in mind is that each channel has its own private ledger. So the Hyperledger Fabric network maintains not just one blockchain, but as many blockchains as there are channels. Every channel, however, makes use of the common infrastructure, including the ordering service. Another important implementation detail is that the smart contracts or chain code will be deployed to a channel. A channel comprises a number of different peers, so when you deploy your chain code, you must specify the channel to which it is deployed, in which case, all of the peers connected to that channel will have a copy of that chain code. Moving along now to the peers of a channel. So each channel, as we have seen, can have multiple members. That is, it can be connected to multiple peers. All of these peers need not be part of the same organization and, as in our example, can in fact span multiple organizations. Another factor is that not all of the peers in the same organization need to belong to a channel. You could have some peers who are part of one channel, other peers who are part of another channel, and so on. This is especially helpful when you have large organizations which may span multiple locations and have several departments, so that only some of those which really need to be part of a channel actually belong to it. And finally, a single peer may also be part of multiple channels. So when a peer becomes part of a channel and some chain code is deployed to it, it effectively becomes an endorsing peer. If you have channels which span organizations, then you may define an endorsement policy such that there is at least one peer from each organization which must endorse a transaction. So with that, we have seen that in Hyperledger Fabric, thanks to the presence of channels, there is a lot of flexibility around keeping transactions confidential. We will now cover one rather important topic in Hyperledger Fabric networks, and this is to do with identity. Since there can be multiple organizations which participate in a single Hyperledger Fabric network, each of them may have their own means of establishing identity, and Fabric is flexible enough to support different sources of identity as long as they stick to a particular standard. In this video, we will take a look at exactly how that works. So, who are the participants in a Hyperledger Fabric network who will need some form of identity? This is something which will allow them to authenticate themselves, and if they happen to participate in any transactions, then those identities can be represented within the transactions themselves. So within Hyperledger Fabric, you have multiple peers which participate in the network, and you will recall from the transaction flow that endorsing peers need to attach their endorsements to a transaction. So there needs to be some way to identify each peer in the network. A Fabric network may also have orderers who again need some form of identity. And then following that, you have individual users as well. These, of course, will include administrators. And beyond that, there are likely to be a number of different client applications which will be connected to the network and will be initiating transactions. A simple solution would be that the Fabric network has its own identity management service, and everyone will need to create a new identity just to work with this network. This is not the approach adopted by Fabric, however, which offers much more flexibility as long as there is a certain standard which is adhered to. And that standard is that identities need to be established using digital certificates. Fabric is meant to be an enterprise-grade blockchain service, and it is also expected that a Fabric network could include multiple organizations. Now, when you have such a system in place, it is possible that each of the organizations will have their own identity management service. And as long as those identity management services issue identities in the form of digital certificates, then it is possible for those same certificates to be used for members to connect to the Fabric network. We have seen this architecture diagram before, where we have a number of different organizations which are connected to the Hyperledger Fabric network. Each organization here has not only several peers, but they may also have their own certificate authority, which will issue certificates within their organizations. And it is those same certificates which can be used to connect to Fabric. How exactly will this work though? This brings us to the concept of a membership service provider in Hyperledger Fabric. The goal of a membership service provider, or MSP, is to establish what the valid identities are for the network. One way to implement an MSP is to have a list of valid root CAs or intermediate CAs, which means that any certificates which are issued by those certificate authorities will be considered valid, and those can be used in order to connect to the Hyperledger Fabric network. Now, it is possible that there is no certificate authority set up in many organizations which still wish to use Hyperledger Fabric, in which case, Fabric includes something known as Fabric CA, which is an implementation of an MSP. This is something which can be used to issue certificates, and then those certificates can be used to establish identity on Fabric. So if you're unfamiliar with the concept, let us take a closer look at certificate authorities. So these are entities whose job it is to issue cryptographically validated digital certificates. These certificates can be issued to individual users, to applications, or even to hosts. A certificate may contain a number of details and does include a public key, and the corresponding private key is also created when the certificate is issued. Someone can say that they trust a certificate if they happen to trust the certificate authority who issued it in the first place. Some well-known CAs include DigiCert, GeoTrust, and Symantec, and these are typically added as trusted certificate authorities by most web browsers. Many websites will have certificates which have been issued by these authorities, and when your browser connects to those websites, it will know that the site can be trusted because its certificate was issued by one of these CAs. Which brings us now to the topic of Fabric CA, which is a component which comes packaged with Hyperledger Fabric. This is a tool which can be used to create certificate authorities in the blockchain network, which in turn will be able to issue certificates. It is these certificates which can be used to establish identity, and do note that the standard which these certificates adhere to is that of the X509 digital certificates. Which now brings us to the question, what exactly are X509 certificates? Well, first of all, it is a digital certificate standard, and this is one which is used by the SSL or TLS protocol. An entity which has been issued the digital certificate will also be given a private key, and its corresponding public key will be present within the certificate itself. By giving the certificate to anyone who wishes to communicate with the website, the traffic between the website and its users can be encrypted using this public-private key pair. And Hyperledger Fabric uses the same mechanism to encrypt any communication on the network. So just to summarize, there are many different identities which will need to be established on Hyperledger Fabric. This includes identities for all of the peers who are connected to the network, the nodes which make up the ordering service, as well as the administrators and clients who will connect to the network. These different entities may be across multiple organizations, and those organizations in turn may have their own certificate authority, which may issue digital certificates for their own applications and their users. As long as those certificates conform to the X509 standard, they can be used to connect to Hyperledger Fabric as well, and for that to happen, the certificate authority issuing those certificates will need to be added as trusted CAs within Hyperledger Fabric. And once that has been done, the certificates themselves can be used to establish identity and to encrypt communication on In this exercise, you will list some of the qualities of an enterprise-grade blockchain network. We covered during this course that Ethereum, for example, is not considered enterprise-grade due to various restrictions. Those limitations have been addressed by the Hyperledger projects while retaining the core functionality of the Ethereum network, which makes blockchain technology so appealing. You will need to identify those characteristics of the Hyperledger frameworks which make them well suited for enterprise use when compared to many of the other blockchain technologies available. Next, you will compare the Hyperledger Fabric network with the Ethereum network. To understand why exactly Hyperledger came up and the properties of Hyperledger Fabric which make it well suited for use across multiple industries and sectors, it helps to compare it with another existing blockchain technology which lacks some of the crucial properties for widespread adoption. So you'll compare both the Hyperledger Fabric and Ethereum networks to draw out exactly what these points of distinction are, which clearly separate the two networks. And finally, you will describe what happens during the execute phase of a transaction in Hyperledger Fabric. Transaction flow on Fabric involves three different phases: execute, order, and then validate. Performing the execution first does help Fabric deliver a very high throughput. However, there is a very specific mechanism which enables this. You will need to recall that mechanism and specifically the steps around the execute phase of a transaction. Each of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task, you needed to list down some of the properties of a blockchain network which can lead it to be considered enterprise grade. Well, one of the most important ones is high throughput. Ideally, such a blockchain network should be able to process tens of millions, if not hundreds of millions of transactions per day. High throughput can be enabled by low latency of the transactions, which means that the entire transaction processing mechanism should be extremely efficient. Enterprises which adopt blockchain technology would like the fees associated with invoking transactions to be either zero or at least predictable. This will better help with their financial planning and is a big consideration for many large organizations. Additionally, enterprises want to make sure that all of their compute resources are used in an optimal manner, and the blockchain network which they participate in should be able to devote most of its resources to transaction processing rather than, say, on solving a mathematical puzzle, as is the case with the proof of work consensus algorithm. Enterprises would also like to control who enters the blockchain network. They may have some kind of vetting process in place so that anyone who enters the network is already trusted, at least to some degree. Not only does this reduce the security risk, there is also far less overhead when it comes to communicating with at least partially trusted nodes as opposed to entirely untrusted ones. Once someone does become a member of the blockchain network, however, it should be possible to regulate what resources they have access to and to what degree. Can they only read from the resource, or can they also write to it? Can an entity invoke transactions on the network? An enterprise blockchain solution should allow the administrators of the network to answer this question rather than provide a prepackaged solution. And finally, to make it easier to develop smart contracts for the blockchain network, it should be possible to define them using some general purpose programming language rather than in a domain specific one. It'll be a lot easier to find engineers who know programming in Python or JavaScript, for example, than in a language which is specific to one blockchain network. We move along to the next task in the exercise, where you needed to contrast the Hyperledger Fabric network with Ethereum. The first point of distinction is in terms of who gets to access the network and become a member. Hyperledger Fabric is a private network, which means that membership is by invitation only. Ethereum, on the other hand, is a public blockchain network, and as long as you have the required hardware and software, you can become a member. In terms of access control, Hyperledger Fabric is a permissioned network, so you can regulate who has access to what and to what degree. This is not the case with Ethereum, where everyone has the same degree of access to all resources. When it comes to cryptocurrencies, the Fabric network has no cryptocurrency at all, and there are no transaction fees, while in Ethereum, the network uses a cryptocurrency called Ether, and that is the unit used in order to pay the transaction fees. When it comes to the life cycle of transactions on these networks, Hyperledger Fabric will first execute, then order, and then validate the transactions. While on Ethereum, the ordering of the transactions takes place first, and then the execution is performed in that order. When it comes to throughput for these networks, Fabric is considered an enterprise-grade blockchain network due to its very high throughput, and this is not quite the case with Ethereum, which can only process about 3 million transactions per day. And when it comes to smart contracts, this is something which is supported on both networks, but in Fabric, you can write your smart contract using general-purpose languages such as Node.js, Java, or Golang, whereas for Ethereum, you need to use a domain-specific language called Solidity. Which takes us now to the final task in the exercise, where you needed to describe the process of transaction execution in Hyperledger Fabric. As discussed, a transaction in Hyperledger Fabric goes through 3 phases. The first of these is the execute phase, which is followed by an ordering phase and then a validation phase. So a transaction is invoked to kick off the execute phase, and this is done by a client application invoking a transaction by sending a transaction proposal to a number of endorsing peers. This is typically done by sending the transaction to a channel on the Fabric network, and then the client application needs to make sure that this proposal reaches enough peers for the transaction to fulfill its endorsement policy. That policy requires that a transaction needs to be endorsed by at least a handful of the nodes in the network, and this policy can vary for each channel. When this proposal is submitted to a channel, all of the peers on that channel will receive a copy of it. And what exactly is within this proposal? Well, this should contain all the information which a peer needs in order to execute the transaction. This will include an identifier for the chain code which needs to be invoked, the name of the function to be triggered, as well as any arguments which that function might have. Multiple client applications will have sent their transaction proposals to many endorsing peers, and once these peers receive the proposals, they can go ahead and execute these transactions. Because the ordering of the transactions will take place only later, it doesn't matter in which order they run the transactions, and in fact, they can even execute them in parallel. This is something which contributes to the high throughput of Hyperledger Fabric. However, to execute the transactions, the peers need to have the corresponding chain code installed. Once that is satisfied though, the peer will execute the transaction and will then attach their endorsement to it. And those endorsed transactions are then returned to the clients which originated them in the first place. And this concludes the execute phase of a transaction's lifecycle on Hyperledger Fabric. The client application can then take those endorsed transactions and then pass them on to the ordering service.